Bienvenidas, bienvenidos a esta cuarta edición de la Escuela Internacional IFUNAM en Frontera de la Luz. Welcome to this fourth edition of the IFUNAM International Schools on Frontiers of Light. Talks will be held in English because we have a few students that do not speak Spanish, and also because we have an international broadcast. However, the inauguration will be held in Spanish. So, vamos a continuar. Estas escuelas son una iniciativa entre la UNAM y el Instituto de Ciencias Fotónicas de Barcelona. Y en la UNAM fue empezada por el Instituto el Centro de Física Aplicada y Tecnología Avanzada, apoyados por la Coordinación de la Investigación Científica. En 2021, también tuvimos a la Universidad de los Andes, que está otra vez en esta edición. El año 2025 ha sido declarado el Año Internacional de la Ciencia, Tecnología y de la Ciencia y Tecnologías Cuánticas por la UNESCO. Por eso, en esta edición, estamos echando la casa por la ventana con varias primeras veces. Es la primera participación presencial del Instituto de Física. También es la primera vez que esta escuela se realiza en el campus principal de la UNAM, en Ciudad Universitaria. Y también es la primera vez que tenemos una sinergia con la Secretaría de Educación, Ciencia, Tecnología e Innovación de la Ciudad de México, que participa con un muy fuerte apoyo. Nos acompañan, bueno, el maestro Guillermo Ayala, que está en camino. Ya llegó. Hola, Guillermo. Qué rápido llegaste. Y también nos acompaña el titular de la Secretaría, Pablo Llanes, a quien le pedimos que nos regale unas palabras.
Bueno, aquí de manera breve, primero un gusto estar con ustedes el día de hoy, en esta mañana, para la SECTEI, la Secretaría que me toca dirigir, pues nos congratulamos de poder apoyar este tipo de iniciativas que además tiene una singularidad porque se da en el marco de los 100 años de la física cuántica y del Año Internacional de la Ciencia y Tecnología Cuántica. Entonces es un doble gusto poderlo hacer. Por cierto, quienes nos acompañan de otros países, en la Ciudad de México estamos celebrando 700 años de la fundación de la Ciudad de México Tenochtitlan, que les extiende una muy cordial bienvenida a esta ciudad fantástica, magnética. Para la SECTEI, pues es un gusto, un privilegio poder apoyar en, en esta cuarta escuela internacional organizada de manera conjunta por el Instituto de Ciencias Fotónicas, la UNAM, la Universidad de en que tengamos más investigación científica y más desarrollo tecnológico, estaremos sentando las bases de sociedades más justas, prósperas y con bienestar. Ayer la jefa de gobierno rindió su primer informe de gobierno e hizo mención a los 100 proyectos de investigación científica y tecnológica que estamos apoyando desde la ciudad, y parte del esfuerzo en esta dirección es efectivamente apoyar todo este tipo de proyectos que además van muy dirigidos, en el caso que nos ocupa el día de hoy, a estudiantes. de desarrollo, una bonita cuarta edición de esta escuela internacional y refrendarles que cuentan con el apoyo del gobierno de la Ciudad de México y de la SECTEI para estas actividades. Muchas gracias.
A continuación, está muy alto, está muy alto. A continuación, hola, hola. ¿Ya mejor? Un poquito más bajo, por favor. ¿Sí? Ok. A continuación, nos va a dar unas palabras el doctor José Luis Aragón Vera, director del Centro de Física Aplicada y Tecnología Avanzada.
Muchas gracias, muy buenos días a todos y a todos. Pues bienvenidos a esta cuarta edición de la escuela IFUNAM, esta vez dedicada a la mecánica cuántica. Ustedes saben, no solamente estamos en el año de la mecánica cuántica, no solamente la mecánica cuántica junto con la inteligencia artificial son las dos áreas de investigación más importantes que se están llevando a cabo en todo el mundo actualmente. Y además el premio Nobel, ustedes saben, esta vez volvió a caer en la mecánica cuántica otra vez, por la observación de efectos cuánticos a nivel macroscópico, ¿no? Un circuito eléctrico. Entonces, pues comienzo con algunos agradecimientos a quienes lo organizaron, a Remy, a Sagún, Daniel Sagún, a nuestros anfitriones, al Instituto de Física, a la doctora Mercedes Rodríguez, al titular de la SECTEI que nos honra con su presencia también, y sobre todo a todas las alumnas y alumnas, a los ponentes obviamente, pero a las alumnas y alumnas que nos acompañan, porque este evento está dirigido justamente a esto. Este evento comenzó, ya tiene varios años, desde que Remy estuvo de sabático en el ICFO. Ahí empezaron a planear la idea de tener una escuela internacional entre la UNAM y el ICFO, e intervinieron varios sectores. No recuerdo ahorita los nombres de todos, me viene a la mente Pablo Loza, por ejemplo, William Lee en México también jugó un papel muy importante. Y en 2019 fue la primera escuela allá en el campus Juriquilla de la UNAM, en el Cefata. Luego en el 2021 ya estábamos en plena pandemia, fue en línea, no tuvo el mismo impacto, pero aún así se celebró. 2023 también en el campus Juriquilla, y ahora pues interviene, desde entonces, desde 2021 ya participó el Instituto de Física, y ahora también pues la alianza con el Instituto de Física es estratégica porque pues ahí se desarrolla, digamos, la investigación más fuerte que se hace en mecánica cuántica en la UNAM. Entonces por eso es muy importante. Entonces, pues no tengo más que agregar más que desearles que tengan mucho éxito, que sea muy provechoso para todo el estudiantado y que aguanten el ritmo porque ya veo que el programa está bastante cargado. Entonces, bienvenidos, bienvenidas, muchas gracias.
A continuación, estará con nosotros la doctora Mercedes Rodríguez Villafuerte, directora del Instituto de Física y que también viene en representación de la doctora María Soledad Funes, coordinadora de la investigación científica. Adelante, Mercedes.
Pues muchísimas gracias, gracias por la invitación y realmente me siento muy, muy honrada de poder compartir esta ceremonia de inauguración con las tan distinguidas personalidades y por supuesto con todos los participantes, profesores que nos honran con su presencia el día de hoy. Como ya comentó el doctor Sagún, vengo en representación de la coordinadora de la investigación científica y le doy la más cordial bienvenida al maestro Pablo Enrique Llanes, titular de la Secretaría de Educación, Ciencia, Tecnología e Innovación, SECTEI, de la Ciudad de México, y al doctor José Luis Aragón, director del Centro de Física Aplicada y Tecnología. Bueno, estimadas y estimados colegas, profesores y por supuesto la próxima generación de líderes en ciencia y tecnología. Muy buenos días. Es un gran placer para mí darles la bienvenida a esta cuarta edición de las Escuelas Internacionales IFUNAM en las Fronteras de la Luz, dedicada este año a la fotónica cuántica. Este evento ha sido coorganizado por diversas entidades de nuestra prestigiosa Universidad Nacional Autónoma de México y el renombrado Instituto de Ciencias Fotónicas de Barcelona, en España. En esta ocasión nos honra realmente contar en esta edición con la participación entusiasta de la Universidad de los Andes en Colombia y en este caso ya se mencionó como institución invitada. También ya se mencionó que esta escuela tiene un significado especial, ya que conmemoramos el centenario de la fundación de la formulación de la mecánica cuántica y se realiza en el marco de las celebraciones del Año Internacional de la Ciencia y Tecnología Cuánticas. A través de los esfuerzos conjuntos del ICFO, UNIANDES y UNAM, en esta escuela buscamos inspirar a la próxima generación de talentosos investigadores en las ciencias de la luz y tecnologías afines. Ya se mencionó, el tema principal es la fotónica cuántica, en donde se explorará la interacción entre la ciencia cuántica y las tecnologías habilitadas por la luz y lo cuántico. Durante esta semana, ya de una vez les advertimos, será una de manera muy intensiva, se cubrirán temas de interés como fenómenos cuánticos fundamentales y preguntas de investigación novedosas y actuales, examinando sistemas cuánticos controlados como arreglos atómicos, materiales bidimensionales y gases cuánticos ultrafríos. Los participantes en esta escuela son un selecto grupo de estudiantes e investigadores jóvenes que provienen de todo el mundo y fueron seleccionados por su excelente desempeño académico y fuerte compromiso con la investigación científica. El objetivo es brindarles una introducción a una área temática de investigación y con una experiencia directa en un entorno científico internacional. El programa está diseñado para fomentar el aprendizaje dinámico y social que va más allá de las conferencias. Se han incluido clases magistrales, seminarios, sesiones de discusión. Tendrán una gran oportunidad de interactuar directamente con destacados científicos a nivel internacional de nuestras diferentes instituciones participantes. Es muy atractivo, de hecho, en que se pueda compartir sus propias investigaciones a través de presentaciones orales y en formato de cartel. También tengo que mencionar que se ofrece una magnífica oportunidad para obtener hasta 2 becas de investigación para estudiantes de licenciatura o maestría con duración de 3 a 6 meses en uno de los grupos de investigación del ICFO en Barcelona, España. Sin duda, esto será un proceso muy competitivo, por lo que espero que su talento e interés les permita acceder a estas oportunidades únicas. Para concluir, quisiera agradecer el entusiasmo y trabajo incansable, y me consta que fueron meses de mucho trabajo, de los miembros del comité organizador. Por parte del IFO, a Robert Sewell y Giovanna Petrillo, a Alejandra Valencia de Uniandes y a Daniel Sagún, Ricardo Gutiérrez, Remy Ávila, Ricardo Román por parte de la UNAM. También quisiera mencionar que esta escuela no se hubiera hecho realidad sin el valioso patrocinio de diversas instituciones, entre las que quisiera mencionar de manera muy particular a la SECTEI, bajo el distinguido cargo del maestro Pablo Llanes, así como de la Coordinación de la Investigación Científica de la UNAM, a través de la doctora María Soledad Funes Argüello. A ambos, mi más profundo agradecimiento. Espero que esta semana sea enriquecedora y estimulante para sus futuras carreras de investigación. Así que siendo las 8:57 horas del lunes 13 de octubre del 2025, declaro oficialmente inaugurada la cuarta Escuela Internacional ICFO UNAM Uniandes Fotónica para la Ciencia y Tecnología Cuántica. Muchísimas gracias.
Bueno, vamos a tiempo, increíblemente. Now it's time to start with some housekeeping remarks. So this is the Wi-Fi name and password. I'm sure most of you are searching for that. Just take a picture. Okay. The other thing is So if you get lost, we have a few hosts around here. You will identify them because they will be have a microphone for the questions. So get close to them if you are not sure about the way to take. Okay, this is registration. We have. I see that a lot of you have done already registration. That's good. For those of you that haven't done it yet, please do so, because otherwise you will not be able to get food. So please, during the coffee break, just go back to the registration office and do it, because you will have some tickets that for every day, for the lunch of every day, that you will have to hand in to the catering people. Okay. About the coffee break, coffee is being prepared in this side of the auditorium. So that logistics will be, if you want to take your coffee up there, that's fine. Or you can also cross the auditorium and have the coffee over there, and then you can go out to the garden. Please do not stay in the auditorium with your coffee. Eating and drinking is not allowed inside the auditorium. The bathrooms, the toilets, are the women toilet are in this side. Men's toilet is this side. Okay. So it's time to begin. Can we swap to the first presentation, please, Danny? So it's my pleasure to start with the first talk of this school. That I'm very pleased that it's given by my good friend Jorge Seman, who has set up a lithium experiment here in Institute of Physics. Some of you will have the opportunity to visit it. That's the other thing that I forgot to say. During the registration, you have to choose which lab tour to take. Please write your name in one of these lists. So because the labs are in different institutes. So Jorge is going to talk. This talk is a part of the quantum matter course, and I'm sure Jorge is going to talk about lithium and Bose-Einstein condensates. His experiment was the first fermionic condensate in Latin America, so it's very interesting. So are we ready to go? Okay, we are sorting out some logistics. Please, the speakers, be aware that we are running the talks in a PC, so we cannot run Keynote. So PowerPoint and PDF are preferred, please. Yes, and please do upload beforehand your talk. Yes. Okay.
It's, yeah. Okay, yeah. Should I move the microphone? That's good. Okay. Fine. So let me start showing you what we are going to be talking about. So I already said this is the first lecture on mainly experimental production, experimental techniques. We use ultra-cold quantum. Next, we will have our colleague Rosario Paredes, also for the Física, giving some remarks on the basic theory to describe them. Next, we have Cabrera, but I know that now he has a different affiliation. We'll be speaking about ultra-cold Fermi gases, ultra-cold Fermi. And finally, early the presentation is here complete. Okay. Okay, better? Okay, very nice. And finally, we have the last lecture by Sarah Hirth. I don't know how to pronounce your last name, sorry. Okay, Sarah will be speaking about a very hot topic in cold atoms, which are optical lattices. It is like a very important system to implement quantum simulators. And also she will be speaking about Rydberg atoms. So let's start. They already told you that this year is the quantum mechanics year. I mean, the year of quantum science and technology. I don't want to repeat it. What I want to show you is the Wikipedia page in Spanish. The Wikipedia page in Spanish has a very nice picture illustrating one of the most important phenomena on here. This is a picture of a Bose-Einstein condensate. If we could switch off the lights, the images will be better. The other way around. It's a quantum superposition. Okay, I think it's better, right? So this is a picture of a Bose-Einstein condensate, and I will explain in a very basic way what this thing is and how this thing is produced. And the first concept that we have to introduce here is quantum degeneracy, okay? So basically, Bose-Einstein condensates is part of a larger family of phenomena that typically occur at very low temperatures. But there are other examples like superconductivity. And what they all have in common is that all of them are quantum macroscopic phenomena. This means they are systems composed by a huge amount of particles that somehow they behave collectively and coherent, and they are described by quantum mechanics and quantum statistics in a global scale. So in general, you can always define a macroscopic wave function that describes the system collectively, okay? And in particular, the concept of quantum degeneracy is fundamental. So I want to start with an intuitive explanation of what it is. But first, I want to be very clear in which is the system I will be considering. It's like one of the simplest many-body system. It's just a gas of atoms, which is composed of atoms, and the gas is very dilute, okay? What does that mean? Very dilute means that the mean separation between atoms, these blue balls are the atoms. The mean separation that I call D is way larger than the interaction range, okay? So the atoms have to be very close compared to D in order to interact. And this is the definition of a very dilute system. And this is important because in this way, the system remains atomic, okay? It's a system made of atoms. These atoms will not, when we cool them down, they will not liquidify or solidify. And also the interatomic interactions will be pairwise, okay? So having three-body interactions will be very unlikely. So interactions are easy to describe, and these systems are easily produced, well, relatively easily to produce in the lab, okay? Okay, now, the first important concept here is the Broglie wavelength. Sorry for the French, the bad French. But what we know, and I am assuming that everyone here has some notions on quantum mechanics, is that particles are described atoms by wave functions, and those wave functions have an associated wavelength. And it turns out that the wavelength is inversely proportional to the momentum of the atom, okay? So atoms that are very hot or that move very fast, like this red atom here, will have a very short wavelength. Those that move slow, they will have, or which have a small value of momentum, will have a larger wavelength, okay? So let us consider this gas. In this gas, this was an animation, the particles were moving. But the idea is that you see that some balls are blue, some atoms are red. You have a momentum distribution. This is a classical gas. These are like the air that we are breathing. And if I take a snapshot with a camera able to see the wavelengths, this is what I see. Most of the atoms will have very short wavelengths if they are hot, but some of them, because it's a distribution, will have a longer wavelength, okay? And in this case, this means that since the temperature and the momentum distribution are related, like this very nice equation, I can also relate the Broglie wavelength to temperature, and we can have this very important concept, thermal de Broglie wavelength, in which we have that the wavelength of the atom is inversely proportional to the square root of temperature. So the colder the atoms, the larger this wavelength. So if I have a gas like the air we are breathing of hot atoms, this means that the interatomic distance is much larger than the wavelength, and it behaves like a classical gas made out of like little balls, okay? If I start to decrease the temperature, what it happened is that the distance, the interatomic distance and the thermal wavelength start to be comparable, and the waves can start to interfere. If the system is very cold, then the wavelengths start to superimpose, and they can interfere, forming this quantum macroscopic wave function that describes the whole system. Okay, so this is why we need to cool them down. But if you have another method to increase the wavelength or decrease the interatomic distance, then the thing is the same. But see that we have a condition to achieve the quantum degenerate state, or this quantum macroscopic state, which is whenever you have a condition of density and temperature in which the Broglie wavelength or the thermal wavelength is larger or equal to the interatomic distance, then you can have interference of wavelengths. And this is why we can relate the density. We can take this product. Density is related to the interatomic distance. And if this number is larger than 1, the system is going to be quantum degenerate. We call it this phase space density. It's a thermodynamic quantity because it depends on density and temperature. And from it, we can extract a critical temperature below which quantum degeneracy takes place. Okay? So let me give you a more precise idea. Basically, what I understand as quantum degeneracy is whenever the concept in these many body systems, the concept of distinguishability, I promise I won't say that word again because I cannot pronounce it. And therefore, the Pauli exclusion principle plays a crucial role to determine how the system macroscopically behaves. And this typically occurs because of the reason I already explained at very low temperature. So when the gas is very hot, I have like a distribution of velocities here in a, for instance, harmonic trap. All right. And here the gas is classic because I don't care if it is made out of fermions or by bosons. Of course, if we cool down, we know that the quantum statistics plays a very important role. We can have, if the gas is composed by identical bosons, then they all can condense in the ground state because they are bosons. There's no Pauli exclusion principle. and the whole system collapses in a single quantum state with a single wave function. And we say, well, this is a very strongly degenerate system because everyone is in the same quantum state. What happens when we have fermions at very low temperature? When we have fermions, they do follow Pauli exclusion principle. So I can only put one fermion per state. And since the system is very old, I can put them only in this, to arrange them in this way in which I start to occupy from the lowest to the highest energy levels in this very ordered fashion. And we have what we call a Fermi degenerate gas, a Fermicide. This thing has several names. And you can ask me, but why this is quantum degenerate if everyone has a different energy and and is occupying a different quantum state? Well, because this definition I'm saying here, this thing is strongly dependent on the Pauli exclusion principle. And this is why we say this is also as degenerate as this one, let's say. Okay. And just let me put some numbers. Typical densities of this extremely dilute gas is of this, like 10 to the 10, 10 to the 12 atoms in as per centimeters. For you to have an idea, the air that we are breathing right now, it's like 10 orders of magnitude denser than so this is very, very, very dilute. Okay. And when you use this density, the critical temperature is of this order, 100 nanokelvin. So this is extremely low temperature. In fact, these are considered to be the lowest temperatures in the universe, in the known universe, and hence, as far as the human science knows, the coldest place in the universe is our planet, in the labs in which these phenomena are studied and investigated. And reaching this temperature was a major technological challenge, which was awarded in 2001 with the Nobel Prize. There are other Nobel Prizes before this, but I just wanted to show this one. Eric Cornell and Kai Wyman from Boulder University in Colorado, Wolfgang Ketterle at the Massachusetts Institute of Technology in the United States. They all produced the first BEC, and they got the Nobel Prize for that. I don't know if I'm standing in the right place. I don't know if the people in this side sees. If I move here is better. Okay, sorry. Okay, so now I hope that you are very curious on how this is done, why this was a Nobel Prize. And of course, if we are going to produce the coldest object in the universe, we have a very clean environment. So we have we have an ultra high vacuum chamber inside which we, in a very controlled fashion, put the atoms, put them down to obtain quantum degeneracy, okay? And basically, any ultra high vacuum system looks like this. There is a science chamber at very low pressure, like 13 orders of magnitude lower than the atmosphere pressure, okay? And here are where we put the atoms and cool them down. We need a source within the vacuum of atoms to, in a very controlled way, take them here. And of course, we need a pumping system to keep everything empty, okay? And there are like millions of ways of doing this. Every experiment is different. It depends on the atom that you want to pull down, or if you have molecules or whatever, and also on the experiments that you want to perform. So let me show you a few pictures. This is a picture that you will be able to see in the visits to the lab. This is the vacuum system of my friend and colleague Asaf Paris-Mandoki, where he produces Rydberg atoms of rubidium. This is something I found on the internet from the Hong Kong University. It's a way more complex system, but all of them have these vacuum pumps. All of them have a vacuum chamber, and all of them, you cannot see it here, but like over here are the source of atoms. It's all the same. And this is a picture of my own system. This is the one that I will be using along the presentation just because I have plenty of pictures. It's not because, even if I think so, it's the best one in the world, but no, it's not because of that. So maybe the picture is not so clear, but the chamber is here. These red things are the pumping stations. The atom source are over here. And as Daniel said at the beginning, we cool down lithium atoms. In particular, we cool down the fermionic isotope, which is lithium-6. This is a picture of the chamber seen from the front view. This is a image of a cut of it, a drawing. This is how it looks from above. And this would be a drawing of how it looks from above. And I'm just, along the whole presentation, I will be using this specific chamber to illustrate ideas so you know what's happening. Everything is happening in the science chamber. So to cool down and manipulate the atoms, I mean, we need to, it's the coldest object in the universe. I cannot put them in contact with something colder, otherwise I would have already finished. I would already have the coldest object. So we need to manipulate the atoms to remove the energy from them. And basically we have a toolbox of things that we can deploy. One is the absorption emission of light. So I have the nuclear. This red ball is the nucleus. The blue thing is the electronic cloud. The atoms might absorb light. They can be excited into some state, and then they might re-emit the light, and I have control on this process. This is used for laser cooling and imaging the atoms. Also, the atoms have a total spin, right? Because they are made out of particles with a spin. They zoom up, and we have a magnetic dipole moment, which is sensitive to magnetic fields. And in this way, using magnetic fields, I can also manipulate them. In particular, we can make magnetic traps. Finally, the atoms, since they are neutral atoms, they in general do not have an electric dipole moment. But if I apply an external magnetic field, then I can polarize the atoms. I can move, I can deplete the electronic cloud and induce an electric dipole moment, which I call D here. And of course, this means that I have two energy terms, one related of the interaction of the magnetic dipole with the magnetic field, and another one coming from the induced electric dipole with the electric field. And I have control of these two terms, okay, in the experiment. So let me start by saying laser cooling in a very intuitive way. So this was a video of someone putting this match in front of the laser, and the match will get fire, will ignite, okay? And this is because light and matter can exchange energy and momentum, all right? And if we have control of this exchange of energy and momentum, typically the matter absorbs the energy from the atoms. And typically matter, when I shine it with light, will heat up. But if I understand the matter, I understand how the atoms are made and which are their electronic levels, and I have a lot of experimental control of light, then I can invert the direction of this interchange, let's say this way. And the main idea is that, imagine I have an atom that absorbs a beam. This atom is moving with certain momentum. At some point, the atom absorbs the light and the momentum changes. It decreases. So the atom cools down or slows down. But of course, because there is emission, you know that the photon will be immediately re-emitted, and like the momentum kick will be, you will have a momentum kick that will only change the direction of the atom. So I'm not effectively cooling it. But of course, I can use a laser beam with trillions of photons and have trillion of absorption and remission cycles. And after this, what I have is that the momentum of the atom will be the original momentum, the momentum transfer due to absorption, and the momentum kicks due to re-emission. The thing is that emission is spontaneous and it's random. So this momentum kick cancels out with this one, and this one with this one, and this one with this one, and this sum is, well, approximately 0. So after n cycles, I have a net transfer of momentum that effectively cools down or slows down the atoms. So what we do is that, of course, the atoms move in 3 directions. So we use 6 beams coming from all 6 directions. Here it's the plane. But of course, there are 2 more beams perpendicular to the screen. And here we can implement something known as optical molasses. This was a video in which some balls will come to the intersection region and slow down, meaning that the system is cooling down. And I'm not showing why, but what it can be shown is that the force that the atoms feel here depend on their velocity, which this is like a viscous force. It's like putting, I don't know, a football ball going through water. It will slow down because of the drag of the water. So here, and a fun fact that the typical deceleration in optical molasses it's huge. It's of the order of 100,000 Gs. And the fun fact is that you will be dead at 20. So it's a huge deceleration. Here I prepared a slide trying to explain in a more precise way what's happening. I don't want to go through it because there's a lot of content. But basically what we do is that we consider a two-level atom. This is a very easy way to understand what's happening, which absorbs light. Okay. And as I already explained it, the force, which is how the momentum changes on time, we know that in average for each cycle of absorption emission, we have a momentum kick, which is equivalent to the momentum of each photon. And this happens in the time in which the transition occurs, which means that this is related to the bandwidth of the transition or the lifetime of the transition and the probability of having the transition. So at the end, I can find an expression for the force that depends on the detuning and the lifetime of the transition, on the properties of this two-level system interaction. And since the atoms are moving, the atoms will see a shifted frequency due to Doppler shift. And at the end, I have a force that depends somehow on the speed of the atoms. That's the idea. If in the questions you want to ask me more, I can go more thoroughly through this slide. But the thing is that when I create these molasses with two beams, then I have two terms of the force. And if I do some approximations here, I can show that this horrible expression reduces into a more into a kinder relationship in which I have a constant that depends on the properties of the light and the two-level system. And what we have is that the force, depending on how the detuning of the light is set, we can have a region in which the force is linear with the speed of the atoms, okay? Now, how is this done in the lab? Basically, you have to understand the energy levels to have control of the emission and absorption cycles. And what I'm going to show here is the case for the alkali atoms, the first column in the periodical table. And all of these atoms, the property that they have is that they behave as hydrogen atoms in which they have many electrons. They can have a lot of electrons like cesium, which has a lot of them, but all of them are arranged in closed shell and they have just one lonely atom in an outer shell. So I can see it like one atom with one electron, okay? And if you check the energy levels, when you consider the fine structure of the atoms, all of them look like this. You have a ground state with the first two excited states, which are a P level, okay? These two transitions are known like the D transition, the D1 and the D2. And if you consider the hyperfine splitting, you have a structure which is very similar to one. And what we use is a cyclic transition, something which was from this state to this state. Notice that the difference is +1. And because of selection rules, the atom, once that it reaches here, the decay is again in this level. So you have the cycling. This is why it's called a cyclic transition. The problem is that also this state can be off-resonantly populated, and you can have a decay here. Of course, we have to put a detuning to compensate the Doppler effect, and we need an extra frequency to repump the atoms that fall down into the state I don't have access with my cooling light. Okay. And of course, more complex atoms might need more frequencies. You need to take account the energy levels or more electrons. But for our alkali, it's very simple. You only need one cooling frequency and one repumper frequency to keep everything cycling, okay? And this is a optical scheme of a typical optical scheme. This is what I have in my lab. These are two pictures. This is distributed into two optical tables. You will have the chance to see it by yourselves in the next days. And of course, laser cooling, and as I told you, is proportional to the speed of atoms, which means that the atoms are not trapped because the force is not dependent on the position, okay? And so what we do is that we apply an external magnetic field, and this external magnetic field adds a term into the force that it's proportional to position. So when the atoms are far away from the intersection of the beams, they feel a force that pushes them back, okay? So I can trap them with the magnetic field, cool them with the optical forces, and this is known as magneto-optical trap. And basically what we do is that we have our molasses, we add a set of coils in the center, we can trap some atoms. This is a more precise idea. I don't want to go through all the slides because these are a lot of equations. The only thing that I want to say is that we have our horrible expression for the forces of the light, and now we have that the tuning will depend also on the presence of the field because the field will split the levels. So now these terms here, they are dependent on a magnetic field, and this is what you get. If you want to ask me, maybe at the end. This was a video, but now it's just a picture of a magneto-optical trap. This ball here is floating inside the vacuum chamber, and this is how it looks, a lithium magneto-optical trap. Okay, now, of course, laser cooling is based on this exchange of energy. Every exchange of something reaches an equilibrium in which you cannot take more than you give, okay? So this means, I don't want to go again into the details, but there is a cooling limit due to cooling, laser cooling. This is known as the Doppler cooling limit, and it depends only on the transition itself, on the on the transition lifetime or the natural bandwidth of the transition. And typically the lowest temperature I can achieve with this scheme of laser cooling is of the order of hundreds of microkelvin depending on the atom, okay? But look, this is 100 microkelvin. This is hell for a Bose-Einstein condensate because this temperature is already the lowest temperature you can imagine if you have never seen something like this. But the thing here is that this temperature is 1,000 times higher than the one that I want to reach. So the atoms are still very hot. Even if this temperature seems low, the gas is still a classical gas. Okay, so what we do is to create a new trap in which there is no exchange of energy, and in which I can use a different technique to keep cooling the atoms down. And what we do is that we focus, this is one strategy, there are others, but we can focus another beam, which is really read the tune from the transition. This means that the atoms will not absorb this beam. There will be no exchange of energy, but they will feel the electric field because light is an electric field. Okay, and I can transfer some atoms from the magneto-optical trap into this purely dipole or purely optical trap. And here I am exploiting this property that I showed you on the beginning, in which I can induce an electric dipole moment and make it interact with an external electric field. The idea is simple. We have that the energy due to this interaction is the dipole moment times dot product with the electric field. But of course, the dipole moment is induced by the field dipole moment. So this dipole moment is proportional to the field. The proportionality constant is known as the polarizability. Tell us how easy it is to polarize, how easy it is to create a big dipole moment. And of course, we know that that this quantity, the square of the electric field, is proportional to the intensity of the beam, is proportional to the power of the beam. So the more powerful beam I use, the deepest the trap will be, or the strongest the force will be. Okay, and one can demonstrate using some math and some approximations that the dipole energy that the atoms feel is proportional to the intensity and inversely proportional to the detuning. Okay, so if I detune a lot, the force will not be very strong, but if I go too close to the resonance, then I will have heating. So you have to find an optimal value here. Or if you have enough power, it doesn't matter. And notice that also the tuning is something I can change because it's the difference between the laser frequency and the internal atomic transitions frequency. So if this quantity is negative, then this will be a negative potential, which means that it will be attractive. I will feel, and the atoms will feel attract where the intensity is the highest, okay? Whenever this quantity is negative. Instead, if I use a blue detuned laser, that means that the frequency of the laser is larger than the frequency of the transition, then this quantity will be positive and they won't see. You cannot see them here, but the atoms are drawn outside. They will see a repulsive barrier and they will be pushed away from the maximum, okay? So basically what I'm saying is if you have a very far detuned laser from the transitions, and you have the ability to create any intensity profile, then you can create any trap you want. Typically, in the experiments, it's very common to use a red detuned focus Gaussian beam, like the one I'm showing here. And this creates a Gaussian potential like this one whenever it's red detuned. So I can trap the atoms here. But of course, since the atoms are going to be very cold, they will only have energy enough to be around this region, which can be approximated like a harmonic potential. So using this type of beams, we can create harmonic traps, okay? Good. Now, how do I cool them down? I just told you how to put them in a new trap. How do we cool them down? Well, these are pictures of how the optical traps look like. This is right in the moment of the transference. This ball here is the magneto-optical trap. This intense line here, it's the beam focus. See how the atoms like to be where the focus of the beam is. And of course, once that I switch off the magnetic field and these lights, all the atoms will go away except those that I trapped along this beam. So I have a very weird beam. Instead of having a spherical thing, I will have a tiny tube, but this is enough. And what we do now is that we selectively get rid of the hottest atoms. Okay, so inside the trap, I have a Maxwell-Boltzmann distribution like this one. Okay, and what I will do is that I will find a way to take away the tail of the hottest atoms. This creates an out of equilibrium Maxwell-Boltzmann, not a Maxwell-Boltzmann, out of equilibrium distribution, which will fastly rethermalize into a new Maxwell-Boltzmann distribution at a lower temperature. And if I keep repeating this, then I can subsequently cool the atoms down. So this was a video, and the video was showing that the height of these walls will subsequently slowly decrease. So the hottest atoms, this atom cannot escape because there is a barrier here. But if I lower the barrier, which means if I decrease the intensity of them, then these atoms can have enough energy to escape. And whatever remains in the bottom of the trap will be cooler, okay? And there are some remarks here. You have to do it slowly because you want the phase space density to increase to achieve quantum degeneracy. But phase space density depends on the number of atoms. So you are losing atoms. The phase space density is decreasing, but also that it depends on, inversely, it depends on the temperature. So if you manage to do this evaporation in a way that the temperature decreases faster than the number of atoms, then you can effectively decrease the temperature and at the same time increase phase space density. And this is how it looks like in the lab. Basically, this is a graph of the power of the beam as a function of time. And as I lower the power of the beam, I have that the phase space density, which is this scale here, starts to increase in a logarithmic way. And at some point of the evaporation, I reach the quantum degeneracy region, and the system becomes a quantum system. Okay? Okay. And now I want to open a parenthesis. Here is the parenthesis. Because I want to explain you how these nice pictures are taken. Okay? And basically, one of the most common techniques is absorption imaging, which means shine the atoms with a beam that the atoms can absorb and make an image of the shadow that the atoms cast on the beam. So basically, what we have is something known as Lambert-Beer law, which means that if I have the medium, I have something, a material, and then I have a laser beam that is moving across it, the intensity of the beam will decrease exponentially. Okay, this is true for dilute systems. And what you have is, I don't want to go too deep into the details, but what you have is that then you can extract the density integrated along the observation axis, okay, which is simply the logarithm of the light after the atoms divided by it's a comparison between the atoms, between the light that passed through the atoms and the light before passing the atoms. I'm seeing how much light I'm losing. And from that, I can create an absorption profile, which is proportional to the density or to the integrated density. So this is a scheme of how this is done. We have the atoms, we shine them with an absorption beam, and the atoms cast a shadow, and then with a lens system, I produce an image of the atoms in this camera. This is how it looks like. I have a picture of the beam with a hole with the shadow of the atoms. I compare it with a beam without the atoms, and then I obtain these very nice absorption profiles, which is proportional to the density. Wherever it is red and intense, the system is very dense, and as it becomes more bluish, the density decreases. Okay. There are other techniques, for instance, fluorescence imaging. So we can shine the atoms again with a laser that they absorb. When they absorb, they re-emit the light. And I can do an image of the re-emitted light. And this is another technique. And what you find is that whatever the intensity of this light that you measure in the absorption, in the camera, is proportional to the density times how much light the system can scatter, okay? And this is a very extremely useful technique, for instance, in optical lattices experiment, because this technique allows you to see individual atoms inside a periodic trap. So for the people using optical lattices, this is the way to go. Finally, this is not an imaging technique, but an analysis technique, which is time of flight technique. Of course, when the atoms are trapped in the optical trap, they are very dense and they are very small. So sometimes you want to release them for the trap and observe how they expand. So for instance, this is the trap with the atoms trapped in the middle. And when we do the image at this moment, we call it in situ imaging, because I am imaging the atoms in situ of the trap. But then I can switch the trap off and the atoms will fall down and will freely expand. And this is useful because I can measure the momentum and the velocity distribution, extract very precisely the temperature of the gas. I can have access to the momentum distribution, which is a very important quantity in the system. It is also useful to resolve very small details like vortices or excitations in the cloud. Okay, so this is a very widely employed technique, and I close the parentheses. Okay, so now we can go back to our optical trap in which we evaporated the atoms. In principle, I already reached quantum degeneracy. And basically, what do we see? Now the question is, what do we see? Okay, I think I'm on time, right? And so how the quantum degenerate gases look like. And of course, what I will see if I cool down bosons or if I cooled down fermions is going to be very different. For both, let me start telling you what happened with bosons. Of course, you cannot produce a T equal to 0 system. You can produce something very close to it, but it will never be 0 because of the third law of thermodynamics. So basically, when you are below critical temperature, you will have that a macroscopic amount of atoms will be in the ground state of the system, but you will have some atoms around. This means that the density that you will extract from the photo that you take will have two parts. We'll have something related to the BEC wave function and something related to the atoms, the thermal atoms, the atoms that are not inside the condensate. And you will have the two things and you need to analyze that. So here there is this is an abuse of notation. What you have is the square root, the square of the norm of the wave function, because it's a complex quantity. But the idea is this one: you have that the density now will be something related to the wave function of the condensate and something related to the thermal distribution of atoms. Okay. And who is this wave function? Well, this is what Rosario tomorrow will explain you. Who is this wave function? How this thing is calculated? What are the equations that you have to solve to obtain it? Just trust me, it exists. It can be calculated. Okay. And this is a series of absorption pictures that I found on this article. I don't have any. This is an erbium BEC from a group in Korea, I think. And I chose these pictures because they are very clear. They are very didactic. This is how a thermal cloud, a cloud that is above TC, the critical temperature, looks like. You have a Gaussian distribution, like a Maxwell-Boltzmann of a classical distribution. This will be the case in which the wave function is 0. Then we cool down, we cross the critical temperature, and at some point you see that you have the Gaussian cloud, like in this broad distribution here, with a very clear peak, which represents the wave function of the condensate, and is proportional. If you keep cooling down, then you can clearly see a bimodal distribution, a thermal distribution of the atoms that are outside from the condensate, and a distribution from the atoms that are inside the condensate. And when you have a nearly pure condensate in which the temperature is much lower than the critical temperature, then you have just the peaked distribution from the condensate. You cannot, it's very difficult to measure the temperature. Picture from the group of Giacomo Roati, and it's not, I don't think you will be able to see it, but this is a Fermi gas. The Fermi gas follows this distribution, and then very slightly here you can see a Gaussian, and the Gaussian it's a bit over this, and then it is exactly over the curve, and then there is a tiny difference here. What I want to say is that the distribution slightly deviates from the Maxwell-Boltzmann thing, so you don't see any spectacular changes. It's kind of boring, this system, okay? Sorry for my friends from condensed matter. Unless you do something which is very nice, which is forming pairs of fermions. And imagine what kind of pair we can form. So now I have a pair, means that the total spin of the system of two fermions will be a integer number, un número entero, okay? And this means that the system now is a boson, or sort of, or a kind of boson, okay? So if you are able to pair the fermions, the pair will condense in a quantum macroscopic state. This is exactly what it happened in superconductors, in which the electrons can pair and form Cooper pairs, and these Cooper pairs are responsible for superconductivity. So a way that you can see it is that you have a Fermi C. You need two spin components for to have this. So you now in the Fermi C have two of each in each level, because now they are distinguishable because they have different spins. But the pairs are formed on top of the Fermi surface, on top of the Fermi C. And these pairs are responsible of the quantum macroscopic behavior in a superconductor. But this is a fermionic property. It's not something that happens with electrons. It's something that happens with fermions in general. So you can also have Cooper pairs with atoms. And at this point, I will, I was avoiding this topic of interactions. Rosario will cover this very profoundly. Also, I forgot to say, but Cesar will be speaking very thoroughly about fermions and how the pairing occurs. But basically, if you consider two fermions, they will interact with an interatomic, intermolecular, potential, which can be something like this. It has an attractive part and a repulsive part. But of course, the system is very cool. Okay, the system is super. It's at nanokelvin. It's much low. The temperature is much lower than the Fermi temperature. This means that the wavelength of each individual atom is huge. In particular, it's larger than this range of this molecular potential. So what I have is that I have waves interacting with other waves whose wavelengths are much bigger than the interaction range. So these waves don't care about the details of this potential. They don't care. So everything, okay, the thing is that the lambda, the wavelength of the wave function describing a single atom, is way larger than the range of the potential. And so the waves, they don't care. When they interact like plane waves, and then they scatter like a spherical wave like this. I'm not explaining the details on this, but if I see the wavefront of the scattering leg of the scattered wave after the interaction, what I can see is that, I mean, I didn't say it, but everything now depends on some parameter that I call a scattering length. I don't care about these parameters anymore. Everything is parameterized by a single quantity. And if I see that the scattered wave is retarded, like this, in relation to this wavefront, then I say that there is an effective attraction and the system is attracting and a Cooper pair can form. If it is the opposite, if this thing turns out into a parameter of interaction that it's larger and you have, and the wave is scattered further away than what you would expect, then you have a sort of repulsion. Is this clear? I'm very aware I'm not explaining this with all the details, but what I want you to understand is that at very low temperatures, the details on the interatomic potential is not so important, and everything can be seen as waves being scattered in a spherical scattered wave. That's how the atoms at low temperatures will interact. And what I'm saying is that the potential that can be very this Lennard-Jones thing with several terms and parameters, I can transform it into an effective potential, which is just like a delta potential, and this is scattering length. And this means that depending on how is the value, that value depends on the atom itself. I can form Cooper pairs if the interaction is attractive, but also if the interaction is repulsive, maybe this is not intuitive, but when the interaction is repulsive, you can show that you can have bound state that associate a molecule, and the molecule is a fermion, and the fermion will condense. You will transform your boring Fermi gas into super fun molecular Bose-Einstein condensate. Okay? So this is the idea, and this is why fermions are so interesting, because you have different quantum macroscopic regimes to explore and play with. And of course, I said that this interaction depends on the properties of the atom, but it turns out that they also depend on the value of an external field. I'm not explaining how this is happening, but basically it's a coupling between hyperfine states of the atom in presence of such magnetic field that will change the way in which the atoms will interact. And basically what you have is that the scattering length, this is the value of the scattering length, depends on a magnetic field in a very strange way, in which there can be a value in which this diverges, and you have regions in which the system is attractive. There are values of magnetic fields in which the system will be attractive, attractive, and you can have something like a BEC, a Bose-Einstein condensate, or something like the BCS, like something similar to a superconductor, but it is neutral. You will have the Cooper pair superfluid, and then you will have something strange in the middle in which the scattering length diverges, and you have pairs whose size are of the same order of magnitude as the interatomic distance. So this will be very strongly correlated. This will be better covered by Cesar. And basically, what you can do is that you can switch your magnetic field. You just spin a knob of a power supply, and you can transform the system into a Bose-Einstein condensate, or into a Cooper pair, or into a Fermi gas, or whatever you want. And then these are pictures in time of flight of our own Fermi superfluid here in Mexico. This was a video of how the Bose-Einstein condensation would appear. And basically, I want to summarize the whole process. I'm almost finishing the cooling process. So we start with a vacuum system with a controlled delivery of atoms to be pulled down. So basically, the atoms will move from the tubes and all the things from the atom source that will be over here. They will move in a controlled way. They will arrive into the chamber. Here we implement the magneto-optical trap. So we pull down and trap some of these atoms. Then we switch on the optical trap, okay? We switch on this conservative trap, and we transfer the atoms from the magneto-optical trap into this thing. And the optical trapping will allow me to do the evaporative cooling, produce the quantum degenerate gas, and will allow me to perform whatever the experiment I want to do with it, okay? Once that the quantum system is produced. And then I will take a picture of the thing. I will do the imaging, the diagnose. Typically, the imaging will be destructive, although there are other optical imaging techniques that I didn't spoke about, which are non-destructive. But typically, this will destroy the super-sensitive quantum system, and you will need to repeat the whole sequence. But in experiments, this whole sequence takes seconds, so you can produce a new superfluid every few seconds. In our experiment, is not so fast. It's one superfluid every 14 seconds, but there are experiments in which you can have one new superfluid every 2 seconds, every second. It depends on the machine, okay? So finally, I want to go through the last section. This part of this section will be better covered by Sarah. I just want you to implant the idea of how quantum simulation can be produced with cold atoms, okay? Because a quantum simulator is a sort of quantum computer. It's not the quantum computer we are used to hear about, and in which you have few atoms or few ions or few superconducting circuits in which you superpose two states, and you have a qubit. We don't have qubits in this type of computer. It's more like an analog computer. But the thing is that I can explore, I can simulate other quantum systems using ultra-cold atoms, okay? And this is because I hope I convinced you that they present an exquisite degree of control. So I like to think about the experiment into a like control thing like this with a lot of knobs and buttons that I can control. Please don't think it's the actual thing. The experiments are complicated. Implementing all these things to be controlled is difficult. This is just an scheme. But basically, what I showed you here somehow is that we can tune interactions through this Feshbach resonance, through this mechanism I showed you. We can create external potentials because we have control of magnetic and electric field. We can change the internal state because we have control on the internal atoms through absorption and emission. We can switch statistics by choosing bosons or fermions, or even starting with fermions and transforming them into bosons. So I have control of quantum statistics. I have control in thermodynamic because I can control the temperature and the density of the system. But I can also have direct access to the wave function through direct imaging. So this is like a wonderful toolbox. It's an excellent platform to study fundamental physics, but also to engineer arbitrary Hamiltonians. In particular, let me remind you, we have control on interactions. We can have whatever type of interaction we want in the system. We can also create any external potential. So we can have this cylindrical trap that I showed you. But if I cross two beams, then I can have a spherical trap. Or if I interfere two beams, then I will have a standing wave. And in the maxima of the standing wave, I can trap things. So I can have a periodic potential. And if I intersect different intersecting beams, I can create a lattice. I can create something that looks a lot like a solid. But I have control of the separation of the atoms. I have control on how the atoms interact, how the atoms will channel from one side to the other one. Tell me which condensed matter system has this degree of control. None. Cold atoms, okay? So basically, this is the idea of quantum simulation, because in the Hamiltonian of the system, I have like full control or nearly full control of all the terms. And finally, I want to say, this is my final slide, that this is a vibrant field of research with very high impact and mostly interdisciplinary interdisciplinary results and the forefront of knowledge. So if you don't know what to do with your lives, this is a good thing. Okay, and I'm showing you just 3 very nice papers from the colleagues that will follow this lecture. One from Rosario, one from Sara, one from Cesar. Just by seeing the titles, you realize that like really hot stuff is going on here. These are very recent papers. And with this, I finish my contribution, and thank you very much.
Thank you, Jorge, for this very nice introduction to the quantum gases course. I'm sure everyone be ready to receive the rest of the information. So we have almost 15 minutes for questions. So please.
Thank you so much. I have a question. When you start, you assume that you have a dilute gas, but you never said that in the experiment. How you assure that the gas is diluted?
So the way that we do that is because we have control on the atom source. Okay, so typically the atom source, I didn't explain that. You are right. It's a receptacle. It's a region in which we put a solid. I mean, lithium, sodium, rubidium at room temperature is a solid, and we heat up this, and the atoms will start to evaporate. So we can control the rate in which the atoms arrive into the trap. Okay, and I can control the rate of how many atoms per second are arriving in the trap. And then the magneto-optical trap is a very it's very big, so the atoms will have a lot of space, and this is how you can tune the density. Okay, also changing the shape of the final trap, the optical trap. In this case, you can also tune a bit the density. And of course, if you have, for instance, a system of bosons with very strong attractive interactions, they can like solidify and you destroy the system. So if you don't pay attention, you can be out from the dilute condition and not able to work with this anymore.
Yeah. Hello, Professor. When you were talking about absorption imaging, you said we only had information about the X and Y position of the density, correct? But you also had an arrangement of lenses which were imaging a certain Z position of the cloud. Are we able to move that arrangement of lenses to image different positions?
Yeah, absolutely. You can. So for instance, here in this image, you have the imaging beam goes on that direction. You only have, you will lose the information along the propagation of the beam, but I can set another image system, for instance, along this direction, I can access to two different orthogonal axes, and I can reconstruct with the part of course, if you have a complicated structure inside the system, imagine that you have a vortex that has a shape, a complicated shape. You cannot rebuild it in that way. There are other techniques in which you use a beam, which is a sheet of light, okay? Una hoja de luz. And then you do a sort of tomography. And then you can reconstruct the 3D profile as well.
So you told us a nice introduction of how you trap the atoms, how you evaporate them, and so on. But could you tell us what you have done in the lab and what plans do you have and what are you doing now?
Sure, I didn't say a word about that. Basically, in my lab, we are interested in studying collective excitations in these systems. Right now, we are studying how sound propagates in a Bose-Einstein condensate. How, for instance, a standing sound wave inside the condensate will behave. This is an old phenomena in nonlinear fluids known as Faraday waves, but we are exploring them for the first time in a Fermi system, in a Fermi superfluid. We are also interested in the next future to study vortices, and because something that I didn't explain also is that the Bose-Einstein condensate is a superfluid as well. So if you produce a vortex, you transfer some angular momentum into the system. This transforms into a vortex, which is quantized. The angular momentum or the circulation of the fluid around the vortex will be quantized. And then if you put a lot of them, you will have some sort of quantum equivalent of a turbulent fluid. And this is one of the research lines that we are pursuing for the future. Is a topic that I really would like to explore with fermions. And this is it. Thank you for the question.
On the last slide, you showed that with optical trapping, you could use an interference pattern to do this trapping with that one. Has there been any work in other types of structural light through that optical trapping, such as structural light, like or optical vortex, to show what kind of things can be done?
So there is plenty of work on this quantum simulation topic. Plenty, and there are many ideas that are explored by people. For instance, there's people that will have they will confine this into a 2D configuration. So instead of having a 3D thing, it's only going to be 2D. And then if you cross the beams in a certain angles, you can transform this square lattice into an hexagon lattice, and you can have something similar to graphene, for instance. Or there's people in which they are able to create like really few sites, like 10 sites or 12 sites, and put a single atom in one of them. And then they can explore, for instance, thermalization at quantum scale with few atoms, how thermalization and entropy behaves like at this very fundamental level. So there are like many ideas. It's a huge field, and we can talk later if you want to know more. And by the way, I'm sure that my colleagues will go deeper into that question.
We'll take the chance to remind you that you have to sign up for the lab tours when you register. I heard that very few people have actually done it. So if you have registered and didn't do that, please go back to the desk and write your name in one list of the lab tours. What else? Just go for coffee. We have half an hour, and remember, don't to put drinks or food inside the auditorium.
Okay, so it is with great pleasure that we're starting our second session of this summer school. Today, I have the honor to present Rocio Jauregui. She's going to be the first lecturer of atomic quantum optics. So with all this, I leave you to that.
I'm very happy to see so many students. Do you listen to me perfectly? No. No. Yeah, better? Or is it? It's okay? The sound is okay? Hello, good morning. Now, do you listen correct? Yes? Okay. Well, I'm very happy to be here and to see so many students. Some of them come from Colombia. Would you please just raise your hand? Welcome to Mexico. Many of them are also from UNAM here. from UNAM. Almost no one is from UNAM. Okay. So I want to thank the organizers for giving me the opportunity to give a pair of lectures about atom optics. It is a very, very broad area, and I will not be able to say many things about atom optics because it's really, really, really very, very huge. And the idea is to give some of the basic concepts and later on give an example, a very particular example that I like a lot. Nevertheless, it's a very particular example of how it can be used to do things that are not so conventional. Tomorrow and the days afterwards, Morgan, Michelle, and Daniel will give us more information of many of the things that I will mention just today. Okay. Then the idea of the talk has 4 steps. The first is to say what do people mean by atom optics. Later, I will mention some of the experimental platforms that are used to implement experiments in atom optics. Very, very concise, very short and brief mention of that. I will also briefly mention the applications because there are so many that I will never will pretend to give everything about these things. And later on, I will just mention a very particular experiment on which atoms, which are called atoms, are scattered by structured light. Many things have been done about trapping, and now I will just talk about scattering with structured light. So the 3 steps are concepts, experiments, applications, and a very particular experiment. Okay. What is the idea in atom optics? In general, in atom optics, what one wants to do is to perform a coherent manipulation of the internal and external degrees of freedom of atomic systems. The name atom optics corresponds to working with atoms. Optics can also be done with other material particles, like, for instance, neutrons, and you could talk about neutrons optics because many experiments have been performed using neutrons, but here I am talking about atoms, okay? And by external degrees of freedom, people refer in general to atomic center of mass. Of course, if you have a very complicated molecule, you have more things to say than just the position of the molecule. But in general, when people talk about atom optics, they just refer to the center of mass motion of the atom. And by internal degrees of freedom, it refers to the internal state of the atom. The idea is to coherently manipulate both of them. Most of the experiments in atom optics started just working with internal degrees of freedom. That is, people were not working on how the center of mass of the atom behaved, but was first interested in knowing how the internal states of the atoms behave. Those kind of experiments were performed together with the board of quantum mechanics. In 1928, already people were working about how to manipulate or how does the internal state of an atom evolve. And one of the examples is the Hubble effect in the 2080s. 10 years later, Rabi was working on how does the internal state of the atom can be manipulated using light. And later on, 10 years later on, 48, Ramsey was using the internal states of the atom to measure time or to perform experiments related, for instance, to the nuclear magnetic resonance. So the idea of working with internal degrees of freedom is very old. It has 100 years or more. And the people has worked with that with a lot of enthusiasm and created a lot of devices to control the internal degrees of freedom of an atom. Later on, and that means the second part of last century, particularly from the 70s, people decided to work also with the external degrees of freedom. Why was necessary to wait many years to work with the external degrees of freedom? The main reason is because the atoms move very, very fast. And it is not trivial to manipulate things that have many whose energy is much larger than the quantum, that required to observe quantum effects. And I don't know, but it would be a nice exercise for the students just to imagine at what velocity an atom enters to their nose when they breathe. And it is very, very high. So the atoms move very, very fast. And that was one of the reasons people were not interested at the beginning to control the center of mass, because they were more interested in knowing what was happening with internal degrees of freedom. In the time that internal degrees of freedom were worked out, people invented the idea of 2 and 3 level atoms, because the atoms are very complicated structures. And in reality, they have an infinite number of states. And under typical conditions, when you want to manipulate, to control the state of the atom, you prefer to focus on just few of the internal states of the atom. And that's why in the 30s and the 40s, it was invited the idea of a 2-level atom. In reality, the atoms have much more levels, but if you just interact with few of them, you control the state so that you mostly 2 of them are the relevant for the description of the system, then you concentrate on the coherent control of those states, and you imagine things like the log sphere describing how a 2-level atoms evolve in time, and the log sphere is just a representation of the internal degrees of freedom of an atom, of a single atom, 2-level atoms, where the density matrix is the important things to describe. Now, one is interested in including external degrees of freedom, that is center of mass. The coherence with respect to the phase of the corresponding de Broglie wave will give you information about the quantum state of the system. If you can control coherently the center of mass motion, then you are able to work in atom optics. That is, you want to work with both of them. In this picture, I am just showing the typical picture of atoms located in an optical lattice, that like the lattice that Jorge told us minutes ago, where the atoms are located at the bottom of some potential, okay? Now, how do you control the center of mass motion of an atom? Well, first you cool it, and then you try to do experiments where the wave nature of these matter waves can be observed. And there are at least two different kinds of experiments. One, when you design gratings, material gratings, where the atoms pass through, and you, on the other side, observe whether or not you have interference effects. Okay? The gratings created with material, with matter, have many advantages over other ways, but it has also one disadvantage. And that is that when the atoms pass through the gratings or near the gratings, they will always experience forces by the surfaces. And this sometimes can be not what you want to do. When you want to observe the nature, the wave nature of matter, and you want just to build things that give rise to diffraction of the atoms without perturbing them. And although the material gratings are very important and have many, many advantages, they also have disadvantages. And how do the people create gratings, material gratings? In this context, the most important things that happen is that nanostructures can be created. And people have learned using lithographic means and gratings with very, very small, nanometer structure. And you can put the pattern you are interested in. You can give texture to the gratings, and you can also diffract almost any atom or molecule. So if you want to make atom optics, that is to control or to study the interference of matter waves, you can do it with material gratings, and everything you will get from this from nanostructures is all these advantages. And the main disadvantages, depends on what you want to do, is that the material lattices function as a way to absorb the atoms, and the transmitted intensity goes down. That's why most experiments, many experiments, are carried out with light. Okay? When you want to coherently control the external decrease of an atom, you can use light, and the idea of using light is very, very good. Already, again, in the 30s, Kapitsa and Dirac predicted that if you send a beam of electrons to a light structure, then you will get, on the other side, diffracted waves. This picture is from the original paper. So the idea of Dirac is just send an electron beam, put a structure with lenses and mirrors that create the pattern here, and the electrons will be diffracted, and you will observe interesting things. Already Dirac thought about that in the 30s. Okay, that kind of experiments was very difficult to do. I told you, because the electrons and the atoms move very fast, and the effects of light are very, very small in general. So you need that the atoms be very, very cool to perform this kind of things, and the electrons to be very, very cold to observe this kind of things. These experiments have been done, okay? And the first time for atom waves was made by David Pritchard in the 80s. And he's perhaps one of the persons that had worked more in atom optics during the last, from 80s to the very recently, okay? The idea is that you send electrons, they are diffracted, and you observe. If you, instead of sending electrons, you send atoms, you can do the same. Okay? There are many, many ranges of interaction that depend on the configuration, the experimental configuration you use to perform this atom diffraction. And using periodic light gratings, there are two regimes that are mentioned or talked about with similarity to what happened in optics. In optics, the Raman-Nath regime corresponds to the case where you observe several diffraction orders in using a grating. And this regime also is found for atoms when they are diffracted by a material grating or a light grating. And there is another regime where the full propagation of the matter wave in the grating yields multi-level wave effects, and then you have to use phase matching conditions to define a diffraction pattern. These are two very different regimes, and one is in general observed, or is mentioned to be observed when the grating is very thick. But when it is very thick, you can have a Bragg scattering, and here you would get the Nathon regime that sometimes is called the Kapitsa Dirac regime. The important point is that light interacting with atoms, and that with light in a periodic array gives rise to diffraction, similarly to what you observe in the case of light, but now the waves are matter waves, and what you observe is the interaction, the diffraction of matter waves. These kind of devices were developed mainly in the 80s and in the 90s, and these kind of devices are typically used in many experiments of atom diffraction. Okay. Now you have a diffracting grating. You can work with thick version, with thin version. You can use very, very atoms, sometimes from Mexico. It's a completely new. This was a prediction that was necessary 50 years to see something. Okay. Now, in general, an atom interferometry experiment requires to have an initial state, split the wave function coherent way in 2 or more states. I was here, okay? So in atom interferometry, you do almost exactly what you do for optics, no? The things are slightly different because the way you you modify the states of the different atoms, is more versatile. Here you can use magnetic fields, you can use another light beams or anything. And in general, what you are interested is to know what happened. Okay. Some of the interferometers that are done in atom optics try to entangle the internal and external degrees of freedom. In some of them, you try to create states where you are not sure about the path and the state at the same time. And this gives rise to many, many interesting features that are being explored technologically in many cases, okay? It is also important to recognize that many of these interferometers take advantage of the recoil effects of the laser beams and also of the use of the external magnetic fields. And it is also important to create different interferometric ways to know traces of these interferometric effects. Okay? Why atom optics is important? Atom optics is important for many things, but perhaps the most well-known concern metrology. And later on, we will have the pleasure to listen to Morgan that will give us a lot of more intuition and many things about metrology using atom interferometry. But I just want to mention that this kind of metrology has led to the best measurements of gravimetry. They are excellent measurements. They give rise to excellent sense of inertial effects. They are, and these inertial effects include rotational effects, so they are also useful for navigation, and testing fundamental physics, high precision of gravity, quantum mechanics. So the applications of atom optics are diverse, and it is a very, very growing area, because every time they measure something with some precision, they look the way to measure it better and better and better, and create better and better and better techniques and learn more about that. And as it is always in physics, the important thing is, what do you ask? Not what you do, but why are you doing it? And many interesting answers have been provided by atom optics. And I hope that during these talks in this week, you will learn more about it. Now I will go to the particular case I wanted to describe in more detail. It is not so important that this case, but I want to describe it because it was done by me. Because well, yes, it is not so important, but I like it. And I hope it will help you to understand some of the ideas, and perhaps later I can give answers about other structural light. What I like a lot to work with optical beams with structure. What do I mean with structure? I mean that they are not the beams that go out from a laser. From a laser, in general, you have beams that can be described within the paraxial regime. They have the waist, they have the Rayleigh length, and that's all. But there are many devices that have been created to give shape to the light. That is, to manipulate the intensity of the light. And they have many ways to manipulate also the polarization. And you can create light with many symmetries, with many configuration, and with many things beyond the optical lattices. The optical lattices are wonderful, but you can do more. Okay? And in general, atom optics with light makes use of the dipole approximations. The atoms, when they do a transition, they couple to the field mostly by the dipole moment of the transition. And the dipole moment of the transition is coded here. And the amplitude of the field is also included in the radius, which is precisely the dipole moment C dot the electric amp. And this dipole moment gives rise to a potential that in the semi-classical limit can be this way. The detuning, that is the difference between the atomic transition and the frequency of the laser, can be manipulated very easily. And here you have the spontaneous decay that is also a characteristic of the transition. Okay, this potential is almost universal, all enough, and you can use it to describe the gross, okay, how does an atom couple to the electric field of an optical beam. Okay, now, if the atoms modify the dynamical properties by this potential, one of the questions I would like to answer, and I don't have the answer, is whether or not the usual dynamical variables that are energy, linear momentum, and angular momentum are the only relevant variables to describe the interaction of light with the structure of atoms with the structure of light. Because in general, I know the energy is related to the frequency of the laser, the linear momentum is related to the k, to the k of a plane wave, and angular momentum is related to the polarization or to the orbital angular momentum if you have vortices in you. But there are also different symmetries in electromagnetic fields, and these symmetries give rise to other dynamical variables. Are they or not relevant in the description of interaction of atoms, center of mass motion, with them? Okay, that is my question. Okay, and to that end, I selected a particular beam. These are beams that have a parabolic symmetry along the x-y axis, like this. This is an obscure zone, and this is an illuminated zone. And they are cylindrical symmetry, so the ideal ones look the same when you take a picture all along the transverse direction of propagation. And these beams have a different dynamical variable. It can be shown that the Weber beams have a dynamical variable, the multiplication of the rotation about the zeta axis and the linear momentum on the z axis. So in this case, we have beams that you can characterize with this parameter. This, that is the wave function that describes the light is an eigenfunction. The electric field is an eigenfunction of this operator. Okay, this picture is a picture of an actual Weber beam created in the lab. It is not a mathematical thing, even though you could get this kind of picture for mathematical anything. Not the point. This is an experimental Weber beam, and this was created using a light modulator, a space light modulator, a phase space light modulator, and the encoding the structure of the beam. And we decided to work this with linear polarization, so it is a very simple beam. But the dynamical constant, the dynamical variable, is different from just angular momentum or just linear momentum. And the question was whether or not atoms interacting with this beam would prefer to be described in terms of this dynamical variable instead of just the linear momentum of the atoms or the angular momentum about the direction of the atoms. That is what's the question. Okay. Okay. Then I had a friend in Germany that told me, if you give the optics, I give the atoms. We didn't have it at that time called atoms in Mexico. So I said, okay, perfect. Joseph, I give you the optics, you give me the atoms, and let's do this experiment. This experiment was done 10 years ago. Sorry for the, well, it is a long time ago. Nevertheless, it is a unique experiment. Here we put a cloud of cold atoms. How cold? They were about 230 nanokelvin. Okay, so they were very, very cold atoms with fluctuation from day to day in the experiment of no more than 5 nanokelvins. It was very impressive quality of the atoms. It was very impressive. And we consider different Weber beams with different aperture here, okay? So the cloud of atoms is here, and you let the atoms, after you have cooled them, you let the atoms go down by gravity. They just fell, okay? You stop the trapping of the atoms are trapped here. Then you switch off the trap and let the atoms fall, okay? And as usual, you take pictures, like the pictures that were described by Jorge just a few minutes ago, at different planes, okay? And do that at different planes that corresponds, in this case, to different times. Because if you let the atoms fall, different planes correspond to different times. And take and see how they fall, okay? Here are the atoms. At the beginning, they are just breaking in 2 waves. Later on, they continue moving to the bottom, and they are partitioned in more structures. And what I am showing here is the experiment and the theory, okay? So we made the calculations with no single open parameter to fit the experiment. They just gave me, I have atoms, this was the temperature, it was the weight, this was the Weber beam, this was what I found, and I did the calculations in my machine, and found this for a lot of pictures, because we did it with different apertures of the parabolic structured light, and we did that with different times of observation, and in general with the same conditions, experimental conditions, so that the clouds were similar at the initial condition, and they develop in different ways, like I showed you. And so we think that the theoretical description is adequate, okay? Because honestly, it's very impressive to have found such similarities without any free parameter, okay? Because we found such similarities, we believe that we were able to use our numerical simulations and make a phase space description of the dynamics. That is, for the numerical simulations, from the numerical simulations, we evaluated the mean value, not the mean value, the expected value of the different densities of angular momentum multiplied by linear momentum. And we found what is in black, and the experimental, because the experiment, of course, was repeated many times. We compared the experiment with theory. And in both cases, we were very happy to find that at short times, we observed that, and at later times, we observed that. And then, when I asked why here you have a parabolic description, while here you have everything very concentrated in a region. And the reason is simple. The atoms are falling, and the falling of atoms is a parabolic falling. So it is not strange that you have both theoretically and experimentally here a parabola, and here something concentrated in some regional space. Okay. From that analysis, we could make and found correlations between the property that the atomic cloud found as a consequence of the falling and passing through the structured light, and the light parameters. And what we wanted to know is whether or not there was a real correlation between what I put in the atoms and what I put in light, and what I get in the dynamic of the atoms. And here are the fitting. of the results. We consider different apertures of the parabola, and that corresponds to different values of the dynamical variable of the light, that is the light parameters. Here is another relevant quantity, of course, was the intensity, the luminosity of the beams, and we also analyze that. And what we have found is that, in general, the atoms acquire a value of the dynamical variable that is precisely correlated to the value of the optical parameter. I mean, this A corresponds to the different values of the dynamical variable of the light. A, 5, 10, 20 corresponds in terms of H bar or well, natural units of this parameter, but for the light, and here is for the atom. We found, of course, that the gravity is important. That's why the numbers increase when you turn off the light. So for long times, you have taken into account gravity, but nevertheless, depending on the value of A, is the value of the theoretical and experimental value of the dynamical variable of the atomic of the atoms. So the general idea behind this work is that perhaps, as physicists, we have learned that energy, linear momentum, and angular momentum are great, but perhaps there are other dynamical variables that should be used in different experiments when you know that they are there, when you know that the symmetry of the system tells you that there are more dynamical variables than the three of them, and light is an excellent source to perform those kind of experiments. In fact, there are 13 different beams for which the dynamical variables are known. And in general, people just work with plain beams. So structured light is important. And what have we learned from this kind of experiments? We have learned that high quality structured beams can be done in the lab. That is not difficult. We have learned that that can be used to create optical lattices or optical slabs, or we can create many things, boxes with light. And that in fact, it is not always important to trap the atoms. Sometimes it is also important to scatter the atoms by structured light, and ask yourself whether the atoms get a given property from such a scattering. It is not, of course, it is important to trap the atoms to play with them, but it is also important to scatter them to study the phenomena. In the case of Weber beams, we found that a Weber beam can be used as a beam splitter, because it split the cloud. We have learned that also you can study and control properties in phase space just using this structured light. And perhaps this platform can be also used to study other things than the traditional ones. And that's all I wanted to talk about.
In the part of atom interferometry, you mentioned that there was a way of to split the waves coherently and then to recombine these components coherently. Is there a notion of partial coherence in atoms in the similar sense that there exists in optical waves and structured light? Thank you.
Oh, okay. You talk about the fracting atoms with light gratings. So in what slides you mentioned about some parameters that you can change on the light? For example, the detuning, that if you want to be on or off resonance. Yes. Yes, but for example, if you are on resonance, you will have effects like the absorption and dispersion. So my doubt is, in what cases you want to be on resonance and when you want to be off resonance?
So you want but if you want on resonance, zero. Listen. So if you want to track some, you don't want non-conservative.
Okay, thank you.
Hi. I wanted to ask that you said that there will be applications of this in the fundamental physics in terms of quantum physics, for example. But as far as I saw in the experiment, we saw that we can measure time versus energy or time versus maybe momentum. But with the uncertainty principle, isn't it going to be much more harder for detection with quantum physics? Because we here see bunch of plots that are specific, but with quantum physics, the Heisenberg principle will cancel those.
Thank you, thank you. Hi, my question is about how long time did the experiment take to demonstrate all the theory, like do all the experiment? Thank you so much.
Well, you said earlier that, well, if you wanted to search or look for new variables, dynamical variables to describe your system, you need to look for symmetries.
So is that something experiment dependent, or do you just wanted to say, well, let's work with Weber beams, for example, or how do you propose, how do you look for those symmetries that could be helpful to describe better the system as you said earlier?
Where show solutions of the equations and numerical values related to this. So, now, and in the other cases, I would also want to that in general, some two beams are modern. Not only non-linear systems. Region I goes so how do you choose?
Thanks.
Have the 13 symmetries of the 13 different solution for the wave equation have been characterized? Do you know how many? Because you guys did for the Weber, and no Laguerre?
Thank you, Rocio, for your lecture. I have a question regarding what you said at the end, that you said that this Weber beam could act as a beam splitter. And I just want to question if that is because we saw on the other graphs that you have like these two blobs as of the. Mm. Okay. Mm.
The variation.
Okay. Okay, thank you. Thank you for your talk, Rocio. I have two simple questions that probably they are related. The first one is why you call it dynamical variable? Is it time involved or is just because you use the momentum here? Why you call it dynamical variables? Okay. Okay. Perfect, thank you. And the second one is when you work and you quantize the electromagnetic field inside an empty cavity, a simple linear cavity, the spatial part of the electromagnetic field is classical and just the time part is that you quantize. In this kind of fields, is the spatial part of your structural light, is it quantum or how do you treat it is my question.
Get right. The focus very, and we wanted to describe this within the quantum regime. Okay? So it was necessary to make a quantum description of structural beams. And that is very, very easy to perform because you just ask, as usual, Einstein idea that the energy of the field must be quantized so that it goes h bar. So the quantization of a structural light is just requires to make the standard idea of saying that a photon, a structured photon, is a photon which has its energy density integrated space of interest goes to h bar. And in this experiment has been performed by Jorge in Germany. We have been working on the behavior of the spontaneous decay within a parabolic. I forgot to mention that light has also.
At the beginning of the talk, you were talking about the interplay between internal and external degrees of freedom. If you were in resonance, can you comment in the what are the selection rules? If I shine this kind of light for an atom, would I expect to have a forbidden transition with this orbital angular momentum, or what happens?
You consider structural beams. Sometimes those beams will prefer to couple to different variables of the matter. For instance, if you have a spherical and the angular momentum of that wave is 2, and the polarization is that the weight, then the coupling will be perfect for quadrupole. In such a case, transitions that are expected to be forbidden, in that case, if you have just illumination with L equal to spherical waves, you expect that quadrupole transitions will be the even more probable than dipole transitions. Okay? Now, in general, the analysis of atom optics has been performed for dipole transitions. And this expression I am giving here corresponds to the Rabi term M C dot E, where M corresponds to the dipole moment of the atom, and E to the intensity of the field. If one is interested in quadrupole transitions, and we have also worked on that kind of transitions, then the quadrupole moment of the atom will couple to the gradient of the intensity. And in fact, we are the Ciencias Nucleares, we have made experiments on quadrupole transitions of rubidium atoms using structural light and non-structural light. And in the way we found a transition that people have not observed before, and we were very happy to see. This is ours, no? And we're working with that. So depending on the structure of the light, you can try to design different, in general, polarization and spatial distribution of the light to try to play with the atomic motions. That is your question.
Yeah, that, and if you could transfer this parabolic momentum to an atom, or it doesn't work.
Yes. But we'll change the expression for the Rabi term, because the Rabi term will come from the couple of the quadrupole moment to the gradient of the field. And in that case, I am not sure whether I would observe what I have observed, because here everything was dependent on the gradient of the intensity and not the gradient of the gradient.
Thank you. So if we don't have any more questions, let's just take a 5-minute break, and then we're going to continue with the 2D materials. Thanks, Rocio.
Hello. Oh, sorry. So we are going to start the afternoon sessions of today, but before, some announcement. So there are some problems with the internet. So the recommendation is please turn off your Wi-Fi unless it's important that you use it, because the talks are being transmitted online. So we need, please don't use too much the internet. Okay, please. What else? I think that's it. And we are going to start. So it is my pleasure to introduce Professor Luis Mochan. So he is from the Institute of Physical Science in Cuernavaca, who is a city close to Mexico City by 1 hour by car. And Professor Mochan is a rock star, actually, from Mexico. He's a rock star on electrodynamics, actually, one of the because he was my teacher. And one of the professors in Cuernavaca said that Professor Mochan was actually the person who knows more on electrodynamics in the entire country of Mexico. Okay, that's his word. So please, Luis, give us your talk. Thank you very much for being here.
Thank you very much, Ricardo. Thank you very much for the introduction, but don't believe a word of what he said. Don't believe a word of what I will say also. I want to give thanks to the other Ricardo for inviting me and allowing me to present this work here. I'm going to talk about classical physics with some flavor of quantum mechanics. So I was not completely sure that it fits into this meeting, but Ricardo Gutierrez insisted that it does. So I will go ahead. So I will talk about homogenization. I wrote it, don't pay attention to my spelling, of multiple component metamaterials. These are some of the collaborators. Andres a student, Raksha was a student, Lucila was also. Guillermo is working in Argentina, in Corrientes. José Samuel Pérez in Zacatecas, and Bernardo Mendoza in León, Guanajuato. So first, let me talk a little bit about the relation of geometry and optical properties of materials. So for instance, imagine that this is a homogeneous metal and somehow you manage to put an excess of charge, say an excess of electrons here in some region. These electrons, they repel each other. So after a while, they will all be flying away from each other, but they have inertia. So even after the system becomes neutral, the electrons will keep on moving, and then we'll have a defect of charge. So if we start with an excess of electrons, later we will have a defect of electrons, and that is a positive charge that will attract all the electrons back. So they will come back again, since they have inertia, they will overshoot and they will start oscillating. And this is a classical version of what a plasma oscillation is. And it has a characteristic frequency, and the frequency is related to the density of electrons, of charge carriers, the charge of each electron, the mass of each electron. So if you make the same, but not within an infinite metal, but in a semi-infinite metal bounded by a flat surface, then everything is the same, but there will be an electric current flowing in this region, and there will be no current flowing in this region. So it is like if you have if you think of this as an oscillator, it's an oscillator where the constant, the restoring force, is half of what it was before, because there is the half of the flow of electrons. So then the plasma frequency, the oscillation frequency in this case, is what we had before, but divided by the square root of 2. If we have a sphere instead of a flat semi-infinite system, then as the electrons move, for instance, if the electrons move vertically in the upwards, then you will have an accumulation of electrons here, and you have the effect of electrons here that will give you a depolarization field. And this depolarization field will pull these electrons back down, and the system will overshoot and it will oscillate. And the oscillation frequency will be, in the most simple model, in the Drude model, it will be the plasma frequency, but now divided by the square root of 3. And if you have many of these spheres interacting among themselves, then this interaction produces further shifts in the resonance frequency. And this has been used since a long time ago. This is the way that these vitrals acquire color with nanoparticles, metallic nanoparticles. This is an even, this is an even older example, the famous Lycurgus, which is made of particles of silver and gold, and which looks green in reflected light, red in transmitted light. It has no pigments, just these metallic particles that have resonances and that interact among themselves. Consider now a dielectric lattice. This would be a one-dimensional superlattice. A wave moving upwards gets reflected by each of these surfaces, and you have multiple reflections. And this makes that photons propagating in this system will have a dispersion relation, which will not be linear as in a homogeneous system. And then you might have gaps where the propagation of light becomes prohibited. If you extend this to 2 dimensions, to a periodic system in 2 dimensions or 3 dimensions, again, you have a photonic crystal, an artificial crystal that has some photonic bands and some photonic gaps. And this has many uses. And this also appears in nature, and it gives color to some of the structures. You have this kind of photonic structures that are responsible for the color in some living beings. Another artificial crystal can be done like this. Imagine you have an insulator plate, and then you deposit metal in these rings, and then you interrupt the rings. So this becomes like an LC circuit, and this LC circuit can resonate. And when it resonates, you have an electric dipole moment across this that looks like a capacitor, but you have a magnetic moment for the current that is moving around the ring. So this, if you calculate or if you measure the macroscopic permittivity and permeability of the system, they have resonances, and above the resonance, they can both become negative. No sé dónde apuntar. Anyway, above a resonance, it is possible that the permittivity and the permeability both become negative, but the index of refraction is given by this product, the square root of this product. So then the index of refraction becomes positive, and you can have propagation in this material, but it's a kind of strange propagation. The dispersion relation in a homogeneous media or homogenized media, the wave vector squared is epsilon mu times the frequency squared divided by the speed of light squared. So if both epsilon and mu are negative, then k is real if the frequency is real, so you got propagation. But it is funny in this sense. If epsilon is negative, if mu is negative, the magnetic field H is opposite to the magnetic density B. So the EB and the direction of propagation of the phase of the wave, they form a right-handed triad of vectors, but EH and S, the flow of energy, is also a right-handed triad. So if H and B point in opposite directions, S and K point in opposite directions, so you get fields that propagate in one direction, the phase moves in one direction, but the energy moves in the opposite direction. And that can be used to make things like these super lenses. Imagine that this is a normal material. This is one of these left-handed materials, that is what they are called, and this is a normal material. So light that is going upwards here gets refracted downwards because the phase is moving upwards, so the energy has to go downwards. So then it goes downwards. When it refracts out of here, it is again refracted, but now upwards. So all of the light that leaves this point converges on this point, so you have a flat lens that actually, in principle, can be diffraction-free. Another example of a system where geometry plays a role is metasurfaces. These are small particles of different shapes that are deposited on a surface. These are particles made of a material with a high index of refraction. So you might choose these particles so that within the particles, since they have a high index of refraction, the wavelength is small. So then even though the particles are small, they can have resonances, kind of me-like resonances. And when you have a resonance, you have a rapid change in the phase of the field as it moves from one side of the particle to another part of the particle. And the phase depends on how close we are to the resonance. So one can use this to modulate the phase of a wave across a surface, and then you can use that to refract light. So for instance, you can have a flat surface here that, depending on the polarization of light goes through straight, or it gets refracted downwards on one, or one can make, no, I didn't show it here, but one can make lenses using this idea, the meta lenses they are called. So what I want to talk to you about is about how to calculate the properties of all of these kinds of systems. And the idea is that these are systems where the geometry plays an important role, not only the composition of the material. So how can you calculate them? One approach, it's not the only one, but there are many, but one approach is to homogenize the system, to change this system, which has particles with a given shape, change it by an effective medium with a homogeneous composition. And then the problem is, what is the response of this effective medium? How do you get the effective response? So you know the displacement is the permittivity times the electric field. If you homogenize the system, if you ignore or somehow get rid of the spatial fluctuations of the field due to the presence of these particles, then you get a macroscopic displacement, which is proportional to the macroscopic electric field. And what we want to get is this macroscopic response. And this macroscopic response is not just the average of the microscopic response, since the fluctuations of the field are correlated with the fluctuations of the microscopic response itself. So the average of the product is not the product of the averages. So one way of proceeding is to find some operator that can be averaged and whose average does have a meaning. So I'll show you this in the most simple case. Imagine, take the displacement field. In general, any field has a transverse component and has a longitudinal component. The transverse component has zero divergence. The longitudinal component has a zero curl. So take the displacement field and just look at the longitudinal component of the electric field, the longitudinal projection. So by definition, its curl is zero, and that is the same as the curl of the electric field in the quasi-static approximation. But I'm just considering here the external electric field. If you take the divergence of this longitudinal displacement field, that is the same as the divergence of the full displacement field, and that is the external charge. And the divergence of the external charge, I made another mistake here, sorry, is just the divergence of the external electric field. So what I want to say here is that the longitudinal projection of the displacement obeys the same equations as the external field. So since it can be identified, the longitudinal displacement is actually the external field. So as it is an external field, it has no spatial fluctuations because it is completely unrelated to the texture of the system. So then instead of writing the electric field, the displacement in terms of the electric field, I write the electric field in terms of the displacement, and then I can average this equation. So I get the average electric field is given by the average of the inverse of the longitudinal projection of the permittivity multiplied by the average of the longitudinal displacement field. And here I can do that because the displacement field has no spatial fluctuations since I took the longitudinal projection. So then these equations allows us to identify what I have here in the middle as the macroscopic response. So the inverse of the longitudinal projection of the macroscopic response is just the average of the inverse of the longitudinal projection of the permittivity. Okay, so, and this can be generalized. So the idea is the macroscopic response to an external excitation, in this case to the external charge, is just the average of the microscopic response. Let me show you how this works in an extremely simple system, which is a binary system, a system made of only two components. So let's call the two components A and B. And epsilon then takes the value epsilon A if we are, say, in the matrix, in this region, in the red region in this picture, and epsilon B if we are in any of these particles. So let us define a function, I call it the characteristic function, that takes only two values, 1 when we are in the inclusion, 0 when we are in the host. So this function tells us all we have to know about the geometry of the system. If we know that function, we know what is the geometry, what is the shape of these particles. All of that is encoded in this function of position. Now, the dielectric function can be written as a function of position in terms of this characteristic function, and it can be written in this strange way. It is epsilon AB, just the difference between the two dielectric functions, multiplied by u minus b, where u is called the spectral variable, and it's given by epsilon of the host divided by the difference in the two dielectric functions. So the idea is that we factor, here we have factored the geometry, which is included in B, and the response, which is included in epsilon AB and in U. So let me go now to a periodic system, to a crystal. So in a crystal, we have a lattice. Whenever we give a step given by a lattice vector, we end up in a place that is similar to the place where we started. And we also have a reciprocal lattice, these vectors, which multiplied by the ordinary lattice gives us multiples of 2 pi. And taking the average is simply averaging in space is the same as taking the wave vector in a Fourier analysis, taking the wave vector equal to 0. So the longitudinal dielectric response, we take the electric response as I showed it to you before, but we just add these longitudinal projector indices, just to remind us that we have to project this function. So this B is just the Fourier transform of the characteristic function I showed you before, but we have to project it into the longitudinal subspace, and then we have to take the average of this. So what is nice about this equation is that this is a Hermitian operator. U is in general a complex variable. So calculating this is analogous to calculating a Green's function. For instance, if you take H as a Hamiltonian in some quantum system, as the Hamiltonian of an electron, and if you take E as a complex variable, then you interpret it as the energy, then the Green's function is the inverse of E minus this epsilon minus H. And what we have to do now is to calculate the inverse of U minus B, where B is a Hermitian operator. So it is very close, this classical calculation to this quantum calculation. And what we need is to get the average, and to get the average is to project onto the states that has a 0 reciprocal vector. So that is the macroscopic state. So what we have to do is calculate this Green's function and project it into the macroscopic state. So that is the recipe that we are going to use. Now we take from quantum mechanics, we borrow the Haydock's recursion method for calculating this projected Green's function. So let me tell you how you do this. We start from a macroscopic state, which is a state which has the reciprocal wave vector equals to 0 and has no other Fourier component. It is just a plane wave with a wave vector that is very small. We apply our Hamiltonian to a given state, and then that gives us a new state. And this new state are orthogonalized with respect to all the previous states. Since H is Hermitian, when I orthogonalize it, I end up with a linear combination of just the last 2 states that I have produced and an actual new state. So this way I can build an orthogonal basis, this N's, which is orthonormal. The product of one of these to any other is a Kroneker's delta function. And in this basis, H turns out to be a 3-diagonal matrix. And the elements of this matrix are just these coefficients, B, A, and B, which are called the Haydock coefficients. And there is a recipe to calculate them. So to get A, I just apply my Hamiltonian and project it to the previous states. And to get B, I just get the magnitude squared of the Hamiltonian acting on the previous state, and I subtract the previous 2 Haydock coefficients squared. So what I do, what I wanted to show you is that this is equivalent to converting any system into a linear atomic chain, right? Because we have our standard starting state. The Hamiltonian evaluated in this state is given by the first Haydock coefficient, but this state can couple to the next state, which is state 1, which is like jumping from an atom 0 to an atom 1. And the coupling coefficient, the Hamiltonian element will be B1. And then the energy on this state is A1. And from here, we can jump back using the same coefficient B1, or we can jump forward using this coefficient B2. And then we repeat from 2, we can jump to 3, to 4, and we can jump back. And what we want is the Green's function of this system projected into this atom. So this is what we want to do. So it turns out, so epsilon macroscopic is obtained from the Green's function of this fake electron in this fake linear. Okay, so I have to multiply by a wave vector, unit wave vector in reciprocal space. Then I have to multiply it by b of g minus g prime and sum over g prime. But if I make a Fourier transform to real space, then this is just multiplying by b of r, and b of r is a trivial function. It just takes two values, 1 when we're in one particle, 0 when we are out of the particle. So this is trivial in real space. And then we can go back to Fourier space and multiply it by this g. And that way we can obtain all the Haydock coefficients, and we don't have to make any matrix operation to do that. I don't know. Okay, so now we don't need the full Green's function. We only need the Green's function projected into a given state, which is the first state. So that allows us to get a formula for the macroscopic function in terms of continued fraction. And the continued fraction has these Haydock coefficients, which depend only on the geometry, and this spectral variable, which depends only on the composition and depends on the frequency. So you have all the information about the composition. We can compute these Haydock coefficients once for a geometry, and then we can make repeated calculations for different compositions and for different frequencies. So this is extremely efficient. And since B is a Hermitian operator independently of the composition, we can apply this for different kinds of materials. We can use it for the electrics, for metals. We can have dispersive materials or non-dispersive. We can have dissipative materials or non-dissipative. Doesn't matter. So we've been using this in my group for a long time. I won't show you the results now. I want to show you the problem of extending it to more complex systems. So what happens is if instead of having a binary system, I have 3 or more materials making the system, then I don't have a characteristic function, so I cannot use the method as I explained it to you before. But we could use directly the dielectric function of this system, the microscopic dielectric function, instead of using B, and use the same kind of formalism. The problem is, in this case, the geometry and the composition are no longer factored, but there is a worst problem. If we have dissipation, then our operator is not Hermitian. And if it's not Hermitian, we cannot build the Haydock basis, and our operator cannot be represented as a 3-diagonal matrix. So in one moment of inspiration, we decided to redefine our internal product. So usually in quantum mechanics, for example, you define the internal product of two states as the integral of one state, one wave function, multiplied by the complex conjugates of the other. But what happens if I do not conjugate it? Then if I make this product in reciprocal space, then instead of conjugating, what I just get is the changing the sign of the wave vector. So this product is the first wave function evaluated at the minus q, where q is a wave vector, which I am integrating over q, and psi I evaluated in the wave vector q. And of course, the sign, I can put the minus sign here instead of here, as I show in the second equation. Well, it turns out that if I use this product, the longitudinal component of the dielectric function becomes symmetric. So here I calculated psi times the dielectric functions times psi would be a double integral. It would be the wave function corresponds to this, the dielectric function multiplied by these two wave vectors to make the longitudinal projection, and then phi on this side, right? So I can, since q is a dummy variable, I can change the sign of q. So this phi becomes this phi here, and this Q becomes minus Q. And if you look at this expression is symmetrical. I can change phi by psi or change Q by Q prime, and it remains exactly the same. So it turns out that even if I have dissipation, the dielectric function can be represented by a by a symmetric operator. In other fields of physics, it is common to use complex Euclidean products that are not without the conjugate. For instance, the divergence of E would be the wave vector times C, but it is not the wave vector conjugated. The same for the reciprocal. When we write the wave equation in reciprocal space, this K squared, it is not the magnitude of K. It is not K conjugate times K, but it's just the direct product of K times K, although K can be a complex vector. So it is not so uncommon to use the Euclidean product with complex quantities. Now I go to a periodic system. In a periodic system, I can, instead of making the two double integrals, I can change one of those integrals by a sum over reciprocal wave vectors and an integral over Bloch wave vectors, where this integral goes is restricted to the first Brillouin zone. So you get something like this. And since the wave vector is a conserved, the Bloch's wave vector is a conserved quantity in a periodic system, then we get, notice we can get rid of the integral. So we get this kind of expression. So notice that this product then mixes Bloch's wave vectors with K with minus K. That means that in this formulation, a Bloch wave that is moving, say, towards the left is coupled to a wave that is moving towards the right. So instead of solving my electrodynamic problem for a single wave moving towards the right or moving towards the left, I have to solve them for both waves simultaneously. So this, in a way, is analogous to these spinors that Dirac introduced with positive energy states and negative energy states. This would be positive wave vector and the opposite wave vector. So I represent my states by this kind of spinor-like quantities. Esto se está acabando la batería, yo creo. De repente salta, de repente. Okay. So then the dielectric response, longitudinal projection, is given by this matrix. It has 0 in the terms that couple K times K and minus K. And the internal product is a non-diagonal because only has terms that include K and minus K. So using this, one can okay. So my initial state would be a single plane wave, macroscopic wave, going in one direction, and the same wave going in the opposite direction. And I can apply the Haydock recursion, as I just showed you before, and build a 3-diagonal matrix, which represents my dielectric response. And then the macroscopic response will be given by a continued fractions in terms of these modified Haydock coefficients. And this can be used for any number of materials. Now, what I want to discuss is a slightly more complex system, which is a system where we have retardation. When we have retardation, we have to take into account that the curl of the electric field is not necessarily 0. So instead of solving the Gauss equation for the displacement field, as I showed you in the initial slides, what I can do is solve the wave equation. So I have a wave operator that, acting on the electric field, gives me the external field. The wave operator is given by the electric function, and the Laplacian with some projection. The Laplacian only acts on transverse fields. So formally, I can solve this equation, multiplying by the wave operator inverse, And since this is the external current, this has no fluctuations, and I can average this equation. If I average, I can identify the average of this term here as the macroscopic wave operator. From the macroscopic wave operator, I can extract the macroscopic, the electric function. So this is the idea. I start from an arbitrary dielectric function that depends on position, but repeats periodically with some unit cell. Using this, I build the wave operator, I invert the wave operator, I average this inverse, I identify this average with a macroscopic inverse wave operator, I invert it again to get a macroscopic wave operator, and from there, I obtain the macroscopic response. It turns out that this macroscopic response depends on frequency, but also depends on wave vector, and it depends independently on the frequency and on the wave vector. So it is a non-local quantity. Its Fourier transform depends on time, but also depends on distance. And from the dependence on K, one can obtain the magnetism, the optical activity, and other things. Well, this is just the announcement. This has been implemented in a program. The program is in the public domain. So if you ever want to use it, you can do it. It's free, it's open. Okay, so the question is, does this work? Okay, so a colleague found an interesting system, which is the cuticle of this kind of box. It turns out that they have a strong metallic reflection, and the light that is reflected by the cuticle turns out to be polarized, circularly polarized, which is interesting. And it turns out that it is the structure, of course, it is a chiral structure, and it is like this. You have a homogeneous layer, and then you will deposit a layer on top that is slightly rotated, and then you deposit a next layer that is slightly rotated. So you have, it is as if you would have many anisotropic layers stacked one on top of the other, and then after a while, the structure repeats itself. So what we did was apply all of this theory to this very simple system, just to see if it works or not. These are called Bulligan structures because Bulligan described them in this kind of animals. And so, sorry. A veces me responde, a veces no. So in principal axis, I will consider only normal propagation. So we have two different electric functions along the principal directions. At different heights, we just have to rotate this electric function. And we have a rotation matrix, which depends on the reciprocal lattice, which is related to the pitch of the system, how long I have to move before the system repeats itself. Okay, this is just a technical thing. We introduced yet another matrix in order to tame the growth of the wave operator for big wave vectors. Don't pay much attention to it. So the Hamiltonian has to be multiplied by this metric, but if I use this metric to calculate these products, then everything is symmetric and works all right. So this is the result. This is the wave vector in the horizontal axis and the electric response in the vertical axis for a fixed frequency. So I fix the frequency in some relatively low value. The frequency is normalized to the, how do you call it? The period of the system is just 1, okay? I have 11 different materials. This is more than 2, so that's what I needed to test the theory. And it turns out that this is the XX component of the permittivity. Turns out to be 1.5, which is just the average of the two permittivities I used to run this test, but it has this parabolic growth. So a parabolic dependence on the wave vector, that is a sign that the system has some magnetism, right? From the second derivative of the dielectric function with respect to the wave vector, one can get the permittivity of this system. And now this is the XX component, which is the same as the YY component. This is the XY component, which is outside of the diagonal. This is the same as minus the YX component. And this is 0, but then grows linearly with the wave vector. So this just means that the system has optical activity, which is not unexpected since we have a chiral system. So we can get the magnetism and the optical activity from this calculation for a small frequency. Now, if I go to a large frequency, in this case, QA, the frequency normalized to the period of the system is 6 instead of being 1. It turns out that we have these resonances. So this is in epsilon XX. And in the off-diagonal response, we also get this kind of resonance. So we have a matricial response that depends on the wave vector with resonances in the diagonal and off-diagonal terms. So what I can do is obtain the eigenvalues of that dielectric matrix, and the eigenvalues have these resonances that are shown here. And the wave equation of the system, the macroscopic wave equation, is that the square of the wave vector divided by this, the frequency normalized to the speed of light, in vacuum. The determinant of this minus the macroscopic response has to be 0. So here you have the wave vector, but here you also have the wave vector. So you cannot solve this analytically in general. But what I did was, in this plot, I have this hyperbola, which is just the inverse of this term. It's q squared, the frequency squared, divided by the wave vector squared. So whenever this line crosses these other lines that describe the eigenvalues of the dielectric response, I have a mode of the system, okay? This is how they look in this low frequency region. And in the high frequency region, we have a crossing here, we have a crossing here. So from this, we can obtain the Green's function, the electromagnetic Green's function of the system, which is here. We have the frequency in the vertical scale and the wave vector in the horizontal scale. And you see it has somewhat confusing. We have this that goes up and then goes down, but it also goes straight. So what I did was analyze this, separated in polarizations, and we have one result for one polarization, in this case, 1I, and we have the opposite result when the polarization is 1 minus I. So this is for circular polarization. So what I want you to notice is that for a given helicity in the system, we have a photonic band gap here, but we don't have the photonic band gap in this direction. So if light, incoming light, turns out to have a frequency within this region, it will be completely reflected, but it will be, the reflected light will be circularly polarized. And if you have the opposite polarization, then it can just go through and penetrate the material. So this explains the optical properties of this kind of insects. This would be for the opposite helicity. So here you have the band gap on the other side. Okay. Well, it turns out that this system is so extremely simple that it can be solved analytically. And the idea is the following. If you take the electric function as a continuous function, the electric tensor as a continuous function of the height, then you have the average electric function times the identity, plus another term that oscillates. Actually, it oscillates with twice the wave vector. That is because the period is actually half of what I told you. because if you are pointing like this and you rotate half a rotation, the system is indistinguishable than from the original direction, right? So half a rotation is the actual period of the system. So then the wave vector is just twice what we had. If I have a circularly polarized light with a given wave vector and act on this wave with this tensor, then what I end up is this term just reproduces the original wave, and this term actually diffracts the wave. So if I have a right circular polarized wave, I end up with a left polarized circular wave, but diffracted by 2g, with the wave vector increased by 2g. And if I start with a left circularly polarized wave, I end up with a right circularly polarized wave, but with a vector k minus 2g. That means that if I start with a plane wave, I get diffracted to only one other wave, but that other wave, since it has the opposite polarization, it gets diffracted into the original wave. So in total, there are only two waves playing any role in this system. So this is what I have here. My plus or minus polarization with a given wave vector is coupled to minus or plus polarization with a wave vector that differs from 2g. And when I apply it again, it comes back. So since there are only two waves, then I can diagonalize analytically the system. The Bloch wave only contains two plane waves, the original one and one diffracted wave. So the wave equation is a 2 times 2 system of equations, and I can have, this would be for the same system, this is the analytical solution, and this is the numerical solution. So you see they are one on top of the other. Okay, so I leave you with my conclusions. We implemented a recursive procedure based on Haydock's representation, the macroscopic response. Actually, I didn't talk about that, but you can get the microscopic fields, can be obtained from this tridiagonal representation of electromagnetic operators. We can obtain the spectra. We generalize this to metamaterials with arbitrary composition and geometry. They might be the electric, metals, dispersive, dissipative. The system is efficient. For binary materials, it is very efficient because the geometry and the response are factorized. It can be generalized to an arbitrary number of phases by changing the Hermitian product into an Euclidean product. But we need a spinor representation, where whenever we consider a wave moving in one direction, simultaneously we have to take into account the wave moving in the opposite direction. So we can use the orthogonality theorems to establish an analogy to Haydock's method. And we generalized this to the retarded case. This yielded spatial dispersion. Spatial dispersion is related to magnetism, to chirality, and it turns out that from the macroscopic response, we were able to obtain photonic bands and photonic band gaps. This is implemented in an open free computational package, and we have tested this generalization, comparing it with analytical results in a system that is attractive because these insects look very nice with their metal-like polarized reflections. So this is what I want to talk to you about. Thank you.
Thank you, Luis. So we have a lot of time, plenty of time to questions to Professor Luis Mochan. Please ask a question. It is your opportunity. People are watching you.
Yeah, well, thank you very much for your presentation. I got a little bit lost in the middle of the presentation. Could you repeat, please, what was the main motivation for redefining the inner product between the wave of
Eh,
and the advantage of doing that?
Yeah, the problem is that when you have a binary system, you have a characteristic function that describes completely the geometry. And that is, you build an operator from that characteristic function, and that operator turns out to be Hermitian, okay? But when you have three or more media, then you cannot define a characteristic function. So you have to use the response itself and have to build everything on top of the response. The problem is that most materials have dissipation. And if you have dissipation, you do not have Hermitian operators. And if you don't have Hermitian operators, Haidok's method does not work. It is made for explicitly Hermitian operators. It was built based on quantum mechanical systems. But if you change the definition of the inner product, then the Haidok coefficients become complex. They are no longer real. But since you have symmetry, then you can make a three-diagonal representation of whatever operator you want to put there. Okay, so the idea is that we are able to inherit the method that was developed using Haidok's procedure. We can use it for systems with an arbitrary number of media, and with media that can have any kind of behavior: metallic, dielectric, dispersive, dissipative, etc. So that was the motivation.
Yes, it's about the photonic, like the computational package. My doubt is if it's just like a library of another language, or it's like a language of code, or what is like the exactly.
The package is it's a long code built using a language that was popular on its time. It's not much popular now, which is Perl. So Perl is a very flexible language. One can make very short, very efficient programs in terms of the time, the developer's time. One can make beautiful programs, one can make horrible programs, you can do whatever you want, but it is not very efficient for numerical work. So then there's a couple of researchers, mainly a group of astronomers in Hawaii, that made an extension to this, to Perl, to this language, which is called the Perl data language. So the idea of the Perl data language is to build a series of libraries or a series of methods for linking programs in Perl to libraries, standard libraries built in ancient languages like Fortran, that are very Fortran, C, C++, whatever, that are libraries that are built with efficiency in mind. So you can have the best of the two worlds. So you can have the expressivity of Perl and kind of like Python, this kind of interpreted languages, and the speed of these old languages, compiled languages. And then on top of that, we used object methodology. So we have an object called Haidok. We have an object that describes the geometry. We have an object that describes the wave equation. And from that object, you can get the Green's function, you can get the dispersion relation, whatever. So the idea is that you build your programs like building with Lego blocks. You choose the blocks you need depending on the characteristic of your system, and then you build in a relatively few lines. You can build a program that calculates whatever you want about the system, and we can calculate we can calculate the macroscopic response, we can calculate the microscopic fields, and we can also calculate nonlinear response based on the microscopic fields. And we have tested with lots of systems. So what is new, which is what I presented you today, is to multi-component systems in the presence of retardation. So we were able to obtain the photonic bands and the photonic band gaps. And it worked in this system that is very simple, but it is trivial to extend it to an arbitrary system with an arbitrary geometry. Yeah.
Okay, thanks so much.
Hello. I just had another question regarding your program and your method. Was it developed entirely at the Institute of Science Physics? I'm sorry.
Sorry, the question is, was it made completely there?
Entirely by your team, yes.
Yes, it was done mostly in the Institute of Physical Science by myself and the group of people I showed you in the initial slides. Some development was done in Corrientes because the members of the group, one of them is in Corrientes, but all the rest was done at my institute, except for something that has been giving me trouble. It turns out that this Perl data language needs to be tested whenever it is modified, has to be tested. So a guy that is currently in charge of PDL noticed my program and decided to use it in order to test the new features of the PDL language. So he started making suggestions to my program to make it more faster, more efficient, whatever. And he pressured me so much that at one point I accepted many of his suggestions without very carefully looking at them. And now I'm suffering for that. But so those were done elsewhere, those changes. They are not changes in the logic of the program, but in the implementation. And there are changes that make it faster.
Well, I have two questions. The first one is, can you put again the graph when you show the band gap?
Sorry, I didn't get the first part of the question, did I?
You put again the graph where
yeah.
show the band gap?
This
Yes.
one?
What happened there in the band gap? It's something like an avoided crossing, or did I understood it wrong? What happened there?
Well, all the band gaps in a solid, in a way, you can interpret them as avoided crossings because you have diffraction, right? So the idea is that the band gap is precisely at this wave vector 2G. Okay? So that is what happens there is that a wave that is moving in that direction can be diffracted into a wave that moves in the opposite direction with exactly the same frequency. Because it has the same wave vector, you just change the direction. So that coupling is what opens the band gap, as happens in solid state physics, right? When you reach the border of the Brillouin zone, is precisely when wave going in one direction are degenerate with waves that are moving in the opposite direction, but are diffracted. So the same happens here. So in that sense, it is an avoided crossing.
And the other question is more for curiosity. When you show the insect with the iris surface, you mentioned that the light gets circular polarized.
Mm-hmm.
It's independent of the light that impacts on the surface of the insect, or?
Yeah, the idea is to, if you shine light that is unpolarized or linearly polarized, you can write it as the sum of light that has one helicity and the opposite helicity. And of those, one of them penetrates and goes through the system, and the other one cannot propagate if the frequency lies within the band gap, so it necessarily is reflected. And since in this particular case, there is no absorption, then it goes back. That's the reason you have the very strong reflection in a small band of frequencies.
Thank you.
Question.
But
Okay, I have a question because I don't understand some things. Why, if we don't have a binary system of more components, why there are no characteristic function that describe the system?
You have one character. The idea of the original method, let me show it. Legalized. So let me see. Yeah. So the idea is this, right? You have one characteristic function. Se movió para el otro lado. Yeah. Okay, you have the characteristic function that takes one value in one medium and 0 in the rest of the material, right? And then you can factor the electric function as something related to composition times U minus B. And here you have the B by itself. You cannot do that if you have more than two materials, right? If you have more than two materials, maybe you could define two characteristic functions, okay? But you won't be able to factor the microscopic response in terms of those two functions itself, right? So you can do, but using tricks and whatever you do, you will end up with the composition multiplying one of those characteristic functions. You don't get something as clean as what we have here. I don't know if that answers. Yeah, okay.
Thank you, Luis. Is this work functions if you use, for example, incoherent light? Is all your approach, does it work if you use incoherent light, thermal radiation, or you need a coherent light? I mean, only plane waves. And because I'm interested on how this works to manipulate incoherent light in probably your photonic media. I don't know if I get the question.
Well, this is a classical calculation. So this is classical light. So then you can do, of course, a superposition of monochromatic. This is classical light and monochromatic light, okay? You can make superpositions, and in that superposition, you can put whatever phase. So you can extend it in a way to incoherent, but I think you're thinking in more fundamental incoherence, right? Yeah, so you could calculate I don't know, the Mueller matrices and whatever using this kind of approach. And yeah.
All right, guys. So we're starting the last part of the day, changing topics a little bit. It is my pleasure to introduce Santiago Caballero Benítez. Santiago studied engineering in physics in El Tecnológico de Monterrey, and then master's up north in Sweden, and then PhD in Australia. So and he ended up in the middle of the world. So we say it is our, bueno, el ombligo del mundo. Okay, so he's going to talk about structural dynamics in dynamical quantum optical lattices. Let's welcome Santiago.
Well, so thank you for the introduction, and now we will proceed with the talk. This is I hope it's not a very difficult talk for you guys, but this is based on current results that we had just published 2 weeks ago in PRL. This project was done with my master's student that just recently graduated, Adrián Ramírez Barajas. He just graduated like some months ago from his master's. And this was done in my lab in the Laboratory of Computer Simulations of Quantum Systems here in the National Laboratory of Quantum Matter
in the Instituto de Física. So, and here I will tell you about what is our problem. Oops. Yeah. No. Okay. So here's the outline of the talk. I will give you some brief motivation why we're interested in these kind of problems. I will tell you about the effective model that we deal with to have strong atomic interactions in cavity and in cavity systems with ultra-cold atoms, and how we deal with solving this problem, which is a very convoluted and complicated from the numerical perspective. Then we introduce the concept of dynamical Wannier functions, and we mix these dynamical Wannier functions with what we call light matter DMRG, which is basically mixing sort of a mean field approach with density matrix renormalization group to actually be able to take into account strong atomic correlations. And then we look at what happens when there are structural phase transitions in the system. And this is motivated by current experiments from the group of ETH, of Tillman Esslinger and Tobias Donner. And we also calculate what it's called the dynamic polarizability, and we look at the modes of thinking of the system, which tells us about what are the properties of the quantum phase transition that we have, and how these different many phases that you will see in the system kind of interrelate to each other, and how we can control actually by light how a phase transition takes place. And I will give you some conclusions about this. So there is recent experiments that we have where we have ultra-cold atoms inside a high Q cavity, and we also have an optical lattices that forms there. And there are many body interactions also there that take place. And we also have light matter interactions. So this is the limit of having a full quantum light with quantum matter. And we're interested in what happens there. And we want to see if there are some analog correlated phases that we know from well-known condensed matter models also, and how these change. The problem here lies in the fact that because basically the box where the atoms live deforms with the energy that we pump into the system. So there is sort of a circus between how the matter correlates with the atoms and the atoms feed back to the light. So typically, what some people have done in the past, including us, like 10 years ago, was to consider that the lattice was a non-deformable entity by the light, so a sort of a static thing. But it turns out that in the actual experiments, this is not the case. So Andy, it's very dynamical, and we need the information of the light, and we need to find this in a self-consistent way. And the problem is that if we try to use regular methods from condensed matter and solid state physics, it is very hard because it's computationally very intensive. So we need to find a way to go around this problem to be able to have something that is computable. And we want to have something that is computable, and that is realistic, right? So that we can predict what actually can be seen in experiment. So that is our main goal. And and we can also see, we want to see if these sort of methods can be used in a more broader sense to simulate light matter systems. And we also want to see, I mean, not in this particular thing that I will show you today, but what it would be the interplay with other degrees of freedom, like internal degrees of freedom. Okay, so this is the old setup that we had 10 years ago, more or less, when we did these papers. And this is the experimental realization of this particular system, which we have the light here of some cavity modes. This is some generalized James Cummings type coupling between the light and the matter, which are the Fs. This is how the Fs are, the matter is coupled. And this is the way that the operators are expanded in some localized bases, where we have here some number operators and we have some tunneling operators. So you can see that already the structure is quite complicated. And basically what we have here is that these couplings here, these G's that we have here, they depend on the Rabi frequency of the light pumping to the system. And we can have in general that this type of model, it can be fermionic or bosonic. Now I mean, when this was done in 2016, where they found supersolids and charge density wave insulators besides from the superfluid and mode insulator, they only had bosonic system, and it was this was rubidium 87 system. Now there's a recent experiment that we have fermions in Lausanne, and so on. Now they are like even they can even address the spin components. So for example, if we want to address spin components, here is taken into account. But here in this particular way of looking at it, we were thinking about some expansion in some non-state dependent Wannier functions, okay? So, and with that already, you can have a plethora of things that can happen. You can have this kind of a three-mode type of structure that can arise besides from having just two flavors, let's say. Okay, and okay, so in general, what we have is depending on the light, let's say the coupling is these J's here, these J's here, depend on the overlap between the cavity mode and the pump mode, and what is the expansion of the Wannier function. So depending on what we're pumping in, if we have a standing wave sort of cavity, we have this kind of pattern, and if not, we have some more complicated, complex functions. But in general, we can think about density modes and some bond modes, what we call here. So these are tunneling processes that inherit the structure of the light. So we have some state-independent wave functions, and these are static. This is the old setting. Okay. So why do we need the new setting? We want to have something that can describe this is the normal phase. So we have just superfluid, but as you can see, it's sitting. The dark here is where the light is, and the white is when there is no light. So here we have the situation where the atoms actually lie when there is no light, and here the system is not super radiant, so there is no emission of light in the cavity axis. And here, well, here it cannot be seen because of the projector, but you could see here that there are some little lines here. So here we have some super radiant emission, and here the atoms localize in this checkerboard pattern like in previous experiments that were done 10 years ago. But now you can also have, and this is coupled to, let's say, the cosine of the light, and this is coupled to the sine of the light with the cosine. So this is a sort of a balanced case, and this is an imbalanced case, which also has some periodic modulation, which is still in the dark, but there is elongated in one particular direction. So we want to have an effective model that can describe this. This has been seen in experiments, and these are the experiments that have been done since 2019. And this is the typical phase diagram. So depending on the cavity detuning and how is the lattice depth that we are with the light that we're pumping, we will see that there is a super radiant region here, and here is a super radiant and another super radiant. And these are different kinds of super radiant states, okay? And this is the latest one, which was just uploaded some months ago, where they have, again, the super radiant phase 1 and super radiant phase 2. Super radiant 1 phase has, the light has pi phase, and in super radiant 2, it has pi halves. And you will see how that arises in a moment. Okay, so, and these are the experiments, and what we ask ourselves is like, okay, what happens now if we have a strong atom-many-body interactions? So interactions by collisions which are strong, which in these experiments were not considered, right? So in these experiments, the interaction between atoms is very small or almost negligible. Okay, so now, so this is the horrible beast that we have to deal with, and it's a horrible beast, right? I mean, it looks horrible, but bear with me and it won't be that horrible, right? Okay, so we have many terms, right? And here we have the cavity photons energy, which is already, I already introduced to you that one. So this AA dagger. And here we're having a monochromatic cavity, right? So it's only one cavity mode. And here we have the kinetic energy atom. So you should be familiar with this. This is just a Laplacian, right? So everybody knows that. Okay. And here we have what we call the pump energy, which is how much energy we're pumping with the light. Okay. And this is some light amplitude times this horrible integral, which is nothing more than some overlap, right? And here we have what is the cavity mode energy, which depends obviously on the amplitude of the light and obviously how the atoms see it. And here we have the interesting bit. So we have the interference of the pump and the cavity in the system. So depending on how I pump the light and depending on how this is aligned with the cavity, we will have a different, let's say, angle, different contributions depending on the angle, which is controlled by this F1 and F2. So typically in the old case, we will only have the F1 term and not the F2 term, okay? And this couples to what is the Q quadrature of the light, and this couples to the P quadrature of the light, just because this goes like sine and the other one goes like cosine, right? So this is like having think about it in terms of an oscillator, which this is in the X direction and this is in the P direction, okay? So it's not so bad. Okay, so this whole thing, if you look at it, it's quadratic in the fields. And because it's quadratic in the fields, it's integrable. And we can suppose that the system is in a Bose-Einstein condensate in the lowest state of energy if it's cold enough. And then we can get around by doing some expansion with basically a plane wave type theory. And that can be done. But the problem is now that if we introduce two-body atomic interactions, that's not the case anymore. And this becomes horrible because then this is not easily integrable, and we cannot use the basis of the condensate because a BEC Bose-Einstein condensate type answers won't describe, for example, insulating phases. And we're trying to find out if we will find insulating phases. Okay, so the message here is like, if I wouldn't have this, then it would be easy. And I would have let's say, a clear path on how to deal with it. Now, because I have this and I have that the manifold of states that would describe the theory of this thing is not only a Bose-Einstein condensate, but something else. Okay, so what do I do? So to deal with this problem of having this with this non-quadratic term, so I do an expansion in the Vanier basis, as I already know from the static case, but now I will allow that these Vanier functions would depend on the state of the light. Because then with taking that into account, I will be able to take a look at the deformation of the box, okay? And if I look at the steady state of the light, and I look at what would be the amplitude of, let's say, the effective coherent state that my atoms will see, it would be something that like this, and this is something that is computable because I just need expectation values of my order parameters in each of the quadratures and this other operator B, okay? So, and then if I go back to this horrible thing, and then I use this expansion, and I group everything together, it looks something like this. So now it's much more simple. So we have basically a Bose-Hubbard model where we have some tunneling here, and we have some many-body interaction, and we have the energy of the modes, and we have some shift in the energy, okay? And these constants here that depend on the light, depend on the state, let's say, by the way that the energy is going to be minimized, okay? But now they also depend spatially because this is on-site terms, and these are off-site terms that give me the probability of the atoms to actually hop from the surface of the energy that it's described there, okay? So this like it is, I still need to solve this problem and then figure out what is the alpha that will minimize this. And then if I know the light, then I need to plug in back and go for them and so forth. So, but the problem is here that I need to know the Vanier functions. So, and I already told you that that's difficult if I use, solid state type of methods, right? Because, I mean, there is software that can be used and everything, but still it's too slow, right? To be able to do it. So what we do is we introduce the notion of dynamical linear functions, and we will solve the auxiliary problem of the matter with DMRG. And this is like a dog chasing its tail. So we will try to guess what's the light in the system. And as we know how the light in the system is, we will turn around and we will compute the energy, and then we will find it in a self-consistent way. So that's what we will do. Okay, and how we do it? We can do it because we use a cheap trick from 1982 from Kivelson, and where he devised a way to actually compute the linear functions in an easy way. Well, more or less easy still, it's a mess, but anyways, this is doable, right? So we need to solve the single particle block Hamiltonian with our effective potential, which is this horrible thing here, right? But then again, that's computable. So we compute that, and then we look at the block states, and then we construct projectors, and out of those projectors, then we look at the bases where we can have simultaneous eigenvalues in the bands. This is a very technical thing, but anyways, the idea is that we find a way to calculate these functions, these linear functions, and we try to do it the best that we can, and then we will try to, using them, we guess first some amplitude of the light, then we compute the verniers, then we again calculate the light amplitude, and then again we get the effective Hamiltonian, and then we go around and around until this converges, and it's actually converges quite fast. And interestingly enough, this just depends on calculating the expectation value of these operators, which is the R1 and R2. And these are already computable once we know the expansion of the block states. Okay? So it is, let's say, a convoluted numerical way of doing it, but it actually is much faster than trying to do whichever other thing that you can imagine. Okay. So, and how do the bands of the potential look like? This is how they look. And we have a problem because if the depth of the potential seen by the effective atoms is too small, then the bands overlap. And if the bands overlap, then we cannot have a well-separated function, linear function. So what we need to do is to not be too small in the depth, but because then, let's say, you're trying to describe a one-dimensional object with a two-dimensional thing. So in order to describe the two-dimensional object is fine if the depth is good enough. But then if it's not good enough, then what you can do is try to do the 1D thing and then interpolate between the two. So that's what we do. And that actually works fine. And so, well, after I told you all these technicalities, this is how it looks like. So in one particular case, we can go from the one-dimensional description, and this would be the linear function. And you can see these are stripes, right? So this is the potential, and this is where the atoms would be. And you can see that in the dark, there are the atoms, right? Nice, pretty. And then here, if I increase the depth, I can get it to be more 2D. So this is, I have more light. And if I have more light, it actually becomes really nice 2D. So I have to go from this to this, okay? And this we compute exactly for this choice, which is that the light is 90 degrees from the cavity. So the pumped light is 90 degrees from the cavity axis, okay? And this is how you can go around it. Okay, so, and this is, for example, we can choose also at 60 degrees, and we can get a different pattern which actually correlates with what can be seen in experiment. And this is the Fourier transform, so that they actually can measure this and it matches. Okay. Okay, so now I told you, okay, I got the verniers, right? But I had to solve the other self-consistent part, right? So I need to solve this problem of the Bossa-Howard model. And the Bossa-Howard model is not easy to solve because I mean, if you want to solve it with a certain degree of accuracy and not in mean field, right? If I solve it in mean field, this is easy, but I need to go beyond mean field because I'm interested in correlations and things that happen when I have a phase transition. So I need to do some more elaborated theory to do it. And to do that, I use DMRG. And what we did is we used this library, this iTensor, and then we constructed this torus geometry, which approximates to a full periodic lattice. And then we average over the tunnelings that we get from the Vanier function calculation. And just to give you an idea, doing this sort of calculation of the maximum number that we did was 98 lattice sites is equivalent to do a Hilbert space of 3 to the power 10 to the 57 with exact diagonalization. So this thing is the nice thing about this is that with some manageable amount of calculation, we can represent something that if we wanted to do exact diagonalization, it would be this size. Okay, so this is very efficient. All right. So just to show you a little bit on how this looks like, when we find this self-consistently, these are the tunneling amplitudes that we get and the amplitudes of the interaction. And this is along these lines. And here I just make a spoof, and this is how the phase diagram would look. And if you look at it, here I'm just showing, I will explain in a minute how this works, but this is very similar to what the experimentalists have, right? So we have some super radiant region, some super radiant region, and some super radiant region. And then I move along those lines. And this is how the tunneling and the interaction changes, okay? Oh, now I will tell you about the phase diagram that I just showed you, but in more detail. But first, I have something that will tell me if the system is 1D or 2D. And for that, I need to compute the interference, either in 1D, the interference between 1D, between the two dimensions, or the spatial pattern in the horizontal and the vertical direction. So here, if I do it for some parameter value of the many-body interaction of the atoms, and I do it in the range of parameters for the experimental system, depending on the detuning. So I will see that in this region, which is super radiant, this is 2D. Here I would see that this is larger, and this is 1D, and this is smaller than this, and this here is smaller than the two of them. So this goes horizontally in this direction here, and this goes in 2D in this direction. This is what it's telling me. Okay. Okay. So now that I showed you the whole thing of how we calculate, so this is what we find. We find some one-dimensional superfluid. This is stripes, right? Which are in this region here. We have a one-dimensional superradiant superfluid, which is this bit here in this region here. We have also that thing here in the tip here. We also have a two-dimensional superradiant superfluid, which is 3, which is here and here. We have the superradiant Mott insulator 1, which is this guy here and this guy here, which is our new results, because previously, as I told you, there were no atom-atom interactions. So now, because we have atom-atom interactions, we can have insulators. So basically, the system is having the atoms fixed in a position, but they are emitting like crazy now. Okay, so that's what happens. And here the phase is pi of the light, and here the phase is pi halves. So here we have a different kind of superradiant Mott insulator, and here we have just superradiant superfluid. So these guys here and these guys here, they were already seen in experiment, but now in new experiments that they will be able to do with potassium 40, they should be able to do the insulators. That's what we found. So before, the insulators were not possible. I mean, they were not computed. Now we predict the actual formation of these insulators. And this is how the light looks like. And this is what the phase of the light looks like. And this is what I was telling you. So here, the phase is pi, and here is pi halves. So if you look at here, the modulus pi, okay? And just to show you that our light matter DMRG actually works nicely, is that here, for example, is if you would do the same calculation in mean field, this is what you would get. If you improve the mean field, this is what you will get. But if you use the DMRG, this is what you would get, and you would see the effect of quantum fluctuations. So the effect of quantum fluctuations shifts the transition point in the phase diagram for the insulators, as one would expect, but now here we compute it, right? And here I show you what is the superfluid component in the system. This part here is the unstable part of the phase diagram when there is no solution. And here you can see that the system is, this is unstable too. So this is superfluid here, and this is superfluid. And in this part, you have the Mott insulator, and here you have the Mott insulator. Okay, so, okay, I showed you now the phase diagram. I told you how I computed. Now I will tell you about some other thing that will tell me information about the system. And it's that I will compute the dynamical polarizability. So for doing that, I need to construct the structure factor. And because my system now is not very deep, so now I have that I need to introduce some corrections due to shallowness. And then I have that my structure factor has some contributions due to tunneling elements, that the tunneling of the atoms that correct, let's say, the simple formula that everybody knows, which would be equivalent to the first term here. And once I compute this, which I can because I can compute these quantum covariance based on the expectation value of these operators in the ground state that I calculate from the DMRG, I can use this trick to actually compute the dynamical part, which is using the expansion in continued fractional representation of the Green's function of a given operator A. And for doing that, I basically need this. So here I will put each contribution of the static structure factor, and then I will need to compute this correction that has all the frequency dependency. And to do that, actually, this is well explained in this paper from 20 years ago. You can actually do an expansion using Krylov methods. And essentially, you approximate this bit doing the calculation of these B1s and B2s and A1s and A0s. And you can go here about, I don't know, we did like 80 excited states of roughly 100 excited states out of the solution from the ground state of the DMRG computing with this operator. And that's how we get the dynamical part of the dynamical structure factor. And once you do that, then you can compute the dynamic polarizability. And why do we want to compute that? Well, we want to compute that because it's visual. So essentially, these guys in ETH, they know how to measure these, and they can compare. And actually, they can measure these type of things, where it tells us about the mode softening. So here, basically, what mode softening means is that if we have two high frequency, as we approach quantum phase transition, or any transition for the matter, as we approach the transition point, then the frequency response of the system should go to the zero frequency. And then as we go away from it, it should open. So this is what we see here for the superfluid multi-insulator transition, which is very pretty, right? And we can also see that depending on the particular structure of the system, we can go from a first order transition to a second order transition or to a weak first order transition, depending if we are in the same symmetry of the problem. And here we can see that because here we don't change much the symmetry, we go from one to weak first order here. So this is the bending here. And here you can see the bending also. And this is along the trajectories of this phase diagram. So this is A, this is B here, and this is C, depending on the, the frequency detuning, right? And this is the arbitrary units of the frequency. And here we can see that there is a jump between this phase to this second order phase transition. And this is because, as you can see here in B, we've changed dimensionality. So because we changed dimensionality, the system jumps, okay? If we are in the same dimensionality, for example, from here to here, which is 1D, the system stays the same. It's still 1D, but there is no jump. So when we change jump from 2D transitions to 1D transitions, it jumps. And when we are in 1D transitions, it doesn't jump, or in 2D transitions, it doesn't jump, which is quite nice, right? And what we actually computed was not this thing, because these things depends on the momenta. Obviously, they can measure to whichever momenta, but because I don't know which momenta they are going to measure, I just decided that we were going to average, and well, this is the average result. And obviously, if they are interested, they can ask us and we can compute to whichever momentum they want, right? And this is how the different order parameters are seen. This is the light in the system. You see here? So depending on which part I'm moving around, you can see how the light builds up. For example, here builds up a little. Here it goes from being very small to being quite big. And then there are all the other parameters in the system. So this is the structure factor when it's maximum, which actually correlates very well to what we have for the condensate fraction, which is computed in the standard way of doing, let's say, the one body to reduce density matrix. And then we estimate how much is the superfluid component there, okay? And here also are the parameters that tells us about the dimensionality and how the dimensionality changes from being 1D to being 2D, and in super radiant 1 and super radiant 2, okay? So it's quite complicated. I know it's a bit violent, but well, that's how it is with this experiment. Anyhow, and well, just to finish, this is the guy that helped me do the computations, Ulises. This is my group, Humberto and Ronaldo and Brian and Cesar. What we do is we do computational simulation and algorithm development for quantum systems. We work with quantum optical lattices and light matter interaction. We do a lot of analog quantum simulation. And I hope I've been able to convince you guys that in these systems, the light changes everything, right? And you can control in whichever way you want, actually, the formation of correlated phases of matter. And it offers an interesting potential to do more interesting theory development and also experiments, which fortunately they are doing. And as I told you, they also have, there are other labs in the world that also do fermions and other bosonic systems. And we hope that this scheme of dealing with the light and the DMRG allows us to go to more interesting problems. And that's it. Thank you.
Thank you so much, Santiago. We have time for questions. Oh, sorry.
Come on, ask something.
Questions? Yes, here.
Hi. You showed us a plot for the superfluid parameter, and it had regions, unstable regions. Can you explain why stable?
Okay. This part here is because it actually turns out in the experiment, this is, and it also happens in theory. What we find in theory when we do our effective low energy approximation of it is that the energy doesn't get minimized for a finite amount of energy. So what happens is that you can plug in as much energy as you want, and the system won't minimize it because the energy surface is just what is it called? Convex. Yeah, so it's the other way around. So it gives you always a maximum. So that's the thing. These could be for two things. We need to take into account probably more bands, or for the approximation of the light, and we need more levels, right? But anyways, in the experiment, they see the same. So the system is not stable in that parameter range. So they see bursts of light that occur in the system. So that's what they see. That's what they've told them. So essentially, the atoms don't have a steady state, but they have something else going on there. Okay. Hopefully, I have been able to answer you.
It is fast. You showed a phase called superradiant, but there was shown superradiant 1 and 2. What's
the difference is this. Look, I have it here. So you see, this is the phase of the light. This is superradiant 1, and this is superradiant 2. Here, the phase is pi halves, and this is because we have the contribution of the sign of the p quadrature, and here we only have basically the cosine part of the coupling of the light with the matter is dominant. That's one.
Thank you. Until which temperatures is the dynamical Vanier function method valid?
Well, this is a t = 0 theory. So essentially, well, we have to have a BEC and it has to be cold enough. So, and basically, if you look at these phase diagrams that we get and you look at the experiment, they are the same. Okay, when the interaction is 0, they're the same. We get exactly the same result. Actually, it's calibrated in such a way that it gives the same result.
Is there a temperature range where the predicted values start diverging significantly from the observations?
Well, the thing is, well, look, these experiments occur in the order of tens of microseconds for each run. So these here, each point, you could think about it that it's so you can have the self-organization and the whole thing for tens of microseconds, and then the system starts to heat up, right? So it depends on how far away you are from the resonance frequency of the atoms, but then again, that controls the lifetime. Okay, so this theory will be valid for some hundreds of nanokelvins. Okay, I won't expect it to be valid for higher temperatures, really. But so far it matches really nice to the experiment.
Thank you. Any more questions?
Nope, buddy.
Yeah. Sorry? The rate of superradiance. What we calculate is actually that we have superradiance. So that we have this, let me go forward. So you can see here that the number of photons actually increased dramatically. So this is of the order of 1,000, right? Okay. So this is 1,000, this is 10, this is 0.1, right? So here we do have superradiance. So the rate, I guess it depends on the rate with respect to what, right? So if you ask me that we can have the rate with respect to the change of the detuning. Obviously here you can just take the derivative of this and off you have it, right? Oh, so it depends on the rate of with respect to what, you ask me. Anything else? No?
Thank you again, Santiago.
Asaf. Hola, hola. ¿Esto lo tienes por tu práctica? Sí. Sí, perdón que me tardé en subirlo. Sí, ya creo que.
Ya, la mañana dije esto.
Ok.
Okay, now it's Asaf Paris Mandoki turn, and he will talk about quantum optics using what? Rydberg.
Superatoms.
Superatoms. Okay, so Asaf studied physics here in UNAM, right? And then you went directly to your PhD in the UK.
Yeah.
And then?
And then I did a postdoc at University of Stuttgart.
Stuttgart.
Yeah.
Yes.
Where I worked mainly on this subject. The things I did before were not related to this, but in the postdoc, it's where I started to work with this. And now,
since 2017, right?
Yeah,
you're at.
I've been building an experiment, and if you want to see it, it's one of the ones listed in the lab tours. So
great. Let's welcome Asaf.
Thank you. Okay, so I know this is the last lecture of a long day, so I mean, it's not easy to pay attention for so long, so I'll try to keep this relaxed and not very heavy. So it wasn't supposed to be that obvious that this was a joke, but anyway. So I tried to put many pictures. Let's hope this works to keep you awake and paying attention, but let's see. So, I mean, the main subject of the talk is to discuss a platform that allows to create tools to manipulate light at the few photon level. So we're going to see how to implement these tools that I'm showing here. So, for example, I mean, these are quantum optics tools. I will shortly discuss each of them, but how to do like on-demand single photon sources, or so it's something that when you press a button, you get a photon out, or single photon subtractor, something that whenever you send certain number of photons, you get one fewer than what you sent in, or a photon turnstile that you send like a bunch of disordered photons, and then, I mean, this is a torniquete. That you send a bunch of photons in disorder and they have to come out one by one. I mean, some of these are more idealized. They're not fully implemented yet, but it's a way to do these things. And then a few photon transistors, something that, I mean, in analogy to an electronic transistor where you have like a small amount of current controlling the flow of a large amount of current. Here we do it with photons that one or two photons control the flow of many, many photons. That's the analogy. So to implement any of these tools, we need photon-photon interactions. I'm going to delve deeper into why we need this. So if you recall from your courses, I mean, the quantum harmonic oscillator or the classical harmonic oscillator, they're both linear systems. If you think about it quantum mechanically, you see that this system has an equidistant ladder of levels, no? So the energy required to go from level 1 to 2 is the same than to 2 to 3, etc. No? That in turns, when you're trying to think about the optical response in a cartoon way about this, you would see that
if you send a single photon, I mean, let's say you start in the ground state for argument's sake, and if you try to excite the system, if you send a bunch of photons which are all the same and in resonance with the system, they will all see the same type of system. What I mean is, it doesn't matter where the harmonic oscillator is in state, it will always require this amount of energy to go into the next level, and that won't change, independent of whatever level you're starting, no? Because of the equidistant levels. This also, like in the classical sense, means that, I mean, the response doesn't depend of what you had already in there. So it's a linear system, no? You know that the classical harmonic oscillator equation, it's a linear equation. So any superposition of solutions is also a solution. So we need a nonlinear to have an effective interaction. So what does that mean? I mean, there's a nonlinear system that it's very easy to get. I mean, every atom is actually nonlinear once you look closer into it. I mean, if you think about a two-level system that starts in the ground state with a single photon, you can promote it to an excited state. And then since it's just a two-level system, a second photon will see a completely different medium, and that it will either create a stimulated emission, but it will definitely won't be absorbed because there's no space for a second photon in your atom. So let's say this is an idealist model. You cannot really order two-level atoms from the store, so you have to use real atoms which have like an infinite number of levels. But in a good approximation, you can use them as a two-level system because they don't have this equidistant ladder of states. No, the energy required to promote it to a first excited state is very different than what you require for an additional excitation. So in practice, I mean, this is really far detuned from the light is very far detuned from the transition. So it's like the interaction is very weak. So any real atom behaves essentially like a two-level system if you control your light precisely enough. So great, atoms are really easy to find, but it's not so easy to build these tools just using a single atom. There you have your nonlinear system, and then what? No, I mean, there's some caveats that it must be a single. I mean, this is an important caveat, that it must be a single, one individual atom. If you use a collection of individual atoms, then you end up with the same system, because perhaps each individual atom by itself is not nonlinear, but if you look at the system collectively, you still end up with the same situation, that maybe this atom gets saturated by the first absorption, but you have all this other collection of free atoms that could absorb your light, and the system collectively still looks like a ladder of levels to the light that you're sending to it. So it's important to have individual atoms. So that's not so easy, how to isolate a single atom. That's the first part of the problem. And actually, this is some nice argument, which actually is from a review of Derek Chang, who will give a talk. I think it's on Wednesday, but it has a lot of details about, I mean, this field, and it's a very good resource. But anyway, I mean, so there's the challenge. We need to use a single atom. It cannot be a collection. And then the question is, how do we couple this atom to the light? Because it's just by, I mean, the naive approach would be like, okay, just grab a couple of grab a lens and focus your light into the atom. But then you're diffraction limited. I mean, you cannot, if you think about the absorption cross-section of the atom and how much you can focus the light, you end up in a situation that you cannot really guarantee that the light will be absorbed by the atom. So you need, I mean, there are a bunch of strategies that are used to improve this coupling and increase the probability that if you send some light, it will definitely interact with your atom. If it doesn't interact, then there's no point in having the atom there to start with. No, so it's important to have the light interact with the atom. So here I just put flash some of these strategies like, oops. So putting this is putting an atom inside an optical resonator is one strategy. So in this case, since you have it in an optical cavity, then the light will bounce around between two mirrors, and then there's a higher chance of one of those times to interact with the atom. There's also to compress the optical mode using you localize the light using like an optical nanofiber. So an optical fiber that's been stretched such that the light is stretched like a bubble gum such that there's a very narrow waist, and then the light will travel partly inside the optical fiber, partly outside, but it's very well confined into a mode. Or even just simply put an atom inside an optical waveguide where the light travels. Or this is like another variant of the resonator one. So such that instead of having two mirrors, you have like a whispering gallery resonator. But anyway, these are strategies to get your atom to interact more strongly with the light. So no, I won't talk about any of this. I'm going to talk about a different strategy, which is to exploit interactions. So, remember that the whole point of this is we want to make tools to manipulate light. And so we need this nonlinear system that will work as a medium so that we have light-light interactions. And then what I'm saying is we will exploit atom-atom interactions to achieve this strong nonlinearity. Okay, so the trick I want to talk about is using Rydberg state. So Rydberg, any highly excited atom, it's called a Rydberg atom. Usually, you can see that some properties, atomic properties, scale very strongly with the principal quantum number you're excited to. So, for example, if you usually a ground state atom is on the order of a few angstroms, while an atom excited to n equals 100. Here I'm talking specifically about rubidium, but the scaling is the same for any atom. But anyway, this specific example, you can see that for an n equals 100, then you have orbital size that it's already 1 micron. There are, I have to think about the scale, but you can see it's like 20,000 times larger than a ground state atom. And also the half-life is very, they live very much longer in these highly excited states. For example, if you excite an atom to this state, this is the ground state of rubidium. If you send it to the first excited state, it will stay there maybe for 20 nanoseconds. And once you send it up to this type of state, to n equals 100, then instead of having 20 nanoseconds, you have milliseconds. So it's several, it's much, much larger. And you can see that the scaling is n to the power of 3. And this is not all. These are some important properties that will help us do experiments, because essentially, this is the time we have to make an experiment before we run into trouble that the atoms are just going back into the ground state. So it's good that they have long coherence times. But the main property that helps us do very strong interaction, that helps us do nonlinear systems, are the strong interactions. For example, the interactions originate from a dipole-dipole interaction. So if you have two atoms, maybe, you have, this is an interaction between neutral atoms. You have two neutral atoms separated by some distance. And it's, I find it easiest to understand it as, it is a second order effect, and this is the way to understand it. You have the atoms separated, they're both neutral, so they're not supposed to interact. But fluctuations, there's always like the fluctuations of the 0-point energy of the electric field. So you can think of these fluctuations maybe let's say, can instantly polarize this atom. If you apply an electric field to the atom, the electron gets pulled away from the nucleus, and then you have a dipole moment here. This dipole moment results in an electric field that then can polarize this second atom, and then as this second atom is polarized, it can the electric field that it generates can affect this one, and so it's this effect results in an interaction that for atoms it scales very strongly. I mean, this is how easy it is to polarize these atoms, 10 to the 7. So, and now the interaction, which is a result of this polarization, scales as n to the 11. So the shape of the interactions we end up having is this it's a C6 coefficient. This is what I'm saying, how it scales, divided by r to the 6. So as I was saying, it's an r to the 6 because dipole-dipole interactions is 1 over r to the 3. And since it's a second order effect, you end up with r to the 6. I mean, and then the way this looks, if you look at the energy levels of the atoms, I mean, here we're talking about a pair basis. So if you grab two atoms, what are their collective energy levels? If they're far away, I mean, this is the two ground state atoms. Then if you excite one to, I mean, I missed to say something in the previous slide, that to excite into the Rydberg state, we usually use two lasers. One, I mean, you don't have to, this is just more practical to do it because otherwise you need a UV laser, which is harder to tame. Optics is harder, generally, it's nicer, and you also have other advantages, which I'll talk about a bit later. But anyway, you need these two photons to excite it to Rydberg state. So here you have two atoms in the ground state, excite one, and then you have one of them in the Rydberg state, or you excite both of them, and you have two in a Rydberg state. In that case, I mean, if they're far away, then there's no effect of the interaction. But as soon as you bring them closer together, then you need additional, because of the interaction, you need an additional energy to create this second excitation. This is an important concept. So what I'm saying is, if you're far away, the same energy to get it here, I mean, you have a linear system, no? The same energy to excite one is the same that you need to excite a second one. But as soon as you bring them close together, the interaction between them causes that if the energy that you use to do the first step is not enough to do the second step. And therefore, the interaction causes a nonlinearity in your system. Okay, I hope that's more or less as clear as it can be at this time. But and what I mean, I just mentioned that the vacuum, the 0-point vacuum quantum fluctuations of the electric field cause this, and it sounds super fancy, but it's just, I mean, it's the same type of interaction, the Van der Waals interaction, what helps to geckos to stick to walls or masking tape to stick to whatever, no? It's just, I mean, it's cool. It's really cool that it's like an effect of the 0-point energy, but it's also like a very common thing to have. And I mean, I won't go too deep into this, but anyway, so what happens with this is like a second cartoon about what happens when you have this interaction. So if you're just working with low excited states where they don't interact, you get this ladder system that I was talking about. No, that you send a bunch of photons, and each atom in the way can absorb a photon, and it looks linear. Now, notice that this arrow is a bit longer than that one, so it can reach up to a Rydberg state. I mean, you don't see, what happened here, this is all distorted because what happened is that this atom was the first to absorb a photon, and therefore this became a Rydberg atom, and the interaction of this atom with its neighbors caused all of the energy levels of the other ones to move away. So therefore, a single excitation in the system caused this it changed the optical properties of the medium completely. One is absorbed and the rest cannot be absorbed anymore. They're very far detuned and the light just goes straight through. So this is what's called the Rydberg blockade, because, I mean, once a photon is absorbed, it blocks the medium from absorbing any further photons. So you can see, I mean, this can have very dramatic effects such that single atoms can, I mean, a single excitation can completely change the optical properties of a medium. Instead, I mean, in conventional linear optics, you need to saturate the medium so that you start getting into nonlinear effects, while in this case, a single photon creates an excitation that modifies the optical properties of thousands of atoms, tens of thousands of atoms, and then it becomes nonlinear like that. Loop. Okay, so what I'm saying is one single photon blocks the absorption of further photons. So this means you can actually, even though you have like a big collection of atoms, if you put them close enough together, this is important. I mean, the Rydberg blockade that I talked about has a distance, a characteristic distance, no? Because maybe if you go far enough away, maybe I should have included that in the picture, but if you go far enough away, like around here, maybe you would have an atom which is still undisturbed. So the interaction of this with the other one won't be enough to detune it, and then maybe here you could have a second excitation, no? I mean, I'm thinking about this decrease here, and maybe around here it's nullified and it doesn't matter anymore. So what I'm trying to convey now is that there's a distance at which this effect occurs. Okay, so then the next step is let's try to pack all of our atoms within that distance. Let's make an atomic cloud really small. Everyone fits inside the blockade radius, and then a collection of atoms can be turned into a single two-level system. So what's the point? You started with two-level systems, and then you end up with another two-level system. But the cool thing about this other two-level system is that it's actually made up of a collection of atoms. It has an extended cross-section, so it's much easier to get your collections of atoms to absorb a photon than what it was to have your single photon absorb a collection of atoms. So by this interaction, you transfer the nonlinear behavior of a single atom to a collective system. So, okay. I mean, it means you don't have to be so careful to isolate a single atom. So now I hope, I mean, that's like the basic principle of how this works. And I now want to try to talk about how that helps us implement some of the quantum optical devices. This is, for example, a single, this is the first one I put, a single photon source. So the way this works, I'll try to be careful at explaining this, is that first, you need to have I mean, the cloud is trapped here with an optical trap and made such that it's in a very narrow space. So you can see that the beam is focused elliptically so that you end up with a sheet of light. And so the point of this is, as I was saying, to pack the atoms inside the Rydberg blockade distance. So then the separation between the atoms within the beam are just smaller than the blockade radius. So this helps. Once you have this atom confined in the light, you can store an excitation in your cloud. Just by doing this 2-photon excitation, you store an excitation in the cloud. What's important, I mean, what's happened, the important part here, let me just finish the scheme. Okay, so you create an excitation, you store it there, and then whenever you want your photon back, you will turn on this third light that by stimulated emission, it will cause this state to decay, and then you'll get this photon out. So first step is to, with these two beams, you store a photon, and with this one, you say, okay, give me my photon back, and this comes out. And so the important thing here is, where did the interaction come into play? Was it in the excitation part? So this excitation, the interaction guaranteed that when I did the excitation, only one excitation was stored. If you didn't have the Rydberg interaction, you would not be able to control how many excitations are in your medium, but this guaranteed that when you excited, it was only a single one. So when you retrieve it, you only get a single one. So this is an on-demand single photon source. This is like maybe, I won't go into too much detail. I mean, maybe for the ones who work with quantum optics, you may be familiar with this G2 correlation function. This tells you, if you detect a photon, what are the chances of detecting another one at the same time? So here it's plotted against the number of the principal quantum number of the atoms used. So if you use, let's say, low excited Rydberg atoms, let's say n equals 30 something, then this means that there's a chance that you get a second photon out. So this is not a single photon source. But as soon as by increasing the principal quantum number used, you increase the interaction, and you isolate this first excitation that you make. So this is with very strong interactions. And then the closer this gets to zero, the more single photon source you have. The more individualized are the photons coming out, let's say. So this was the single photon source. Let's go to some other device. I also mentioned this single photon absorber. This was this medium that you send n photons and you get n-1 out. The trick here, it's similar to the single photon source, except that, I mean, what you want, I didn't go, when I was talking, I mean, here I'm talking about the two-level system where you have the ground state, and this is like the collective Rydberg excited state. I mean, here I'm glossing over many, many details, but this is the two photon excitation. And what you want is that you can think that once the medium is saturated, it absorbs the photon, it's saturated, so then it won't absorb a single photon. The trick here, I mean, what is a bit tricky is that if you just had the two-level system, you could not do a single photon absorber, because if you have a two-level system, what do you think it will happen if you absorb one photon and then you send another photon of the same kind? It will be, I mean, there's a problem. The first photon that you send won't stay there, because if you just have the two-level system, it will absorb a photon, and then the second photon will create a stimulated emission, and then you would lose your absorbed photon. And instead of having a photon absorber, you will get something that will just do Rabi oscillations. So, I mean, what you need to do is something that is very against the policy of experimentalists usually, that it's to introduce noise into your system. Usually, all the effort is to get rid of noise, and here it's more like, let's put some noise into the system such that whenever you get an excitation, the state moves to, I mean, the noise causes the state to move into other dark states that are not coupled to the light, but these are still Rydberg states. And then you have like a blockaded system that it's not, I mean, what will happen is you absorb a photon, noise drives it to a dark state, and then, but these, I mean, both of these are Rydberg states, so it will still be blocked, and it will not absorb another one. But the noise is very important so that you don't get stimulated emission. I had some plots, but those are more for morning talks. So if you want to, they're at the end if you want to, if you feel very energized and you want to see like the minutia of all this. But the single photon counters, no, this is the experimental implementation of the single photon absorber. So what you do, I mean, it's just, what's important is to get the cloud really small, confined, and have so that every atom is within the blockade radius. Otherwise, if you have an atom outside the blockade radius, like the imaginary atom I was pointing out here, that it's outside the blockade, and then it will be a second excitation available. So you need to make the cloud small so that only a single photon fits in the cloud. And I mean, it's basically playing trickeries with traps, such that maybe you start with a trap like this, you add some additional beams such that you end up with the red stuff is the atomic density. These are pictures of atomic clouds, which are produced here. I didn't go into details of that, but all these experiments have to be done with cold atoms, because otherwise Doppler effect can be bad for what things we want to do. So this is usually done with around 4 microkelvin, a few microkelvin cloud, making the cloud really small and going to very high Rydberg state, so 111 state. And usually around this cloud, there are 10,000 atoms. So that means a single excitation changed the optical properties of 10,000 atoms in this case. So, this was how to implement the single photon absorber. So it's basically just smoosh your cloud a lot and use a high Rydberg state and add some noise. That's the recipe. Another implementation, now here I'm just going through different tools, but the few photon transistors, another interesting application of this. This is a bit more complex, but let's say, maybe here I'm missing some more context, but you can set your atoms such that, the green stuff, it's supposed to be your cloud of atoms, and you can configure it such that the light passes through the atoms. Maybe you adjust the frequencies of your laser such that the atoms go through the light. The light goes through the atom. Sorry, I'm mixing things up. However, you have this situation, but you can create another situation where if you create a Rydberg excitation, what allows the light to go through your cloud is their frequency. But if you create a Rydberg excitation that changes the optical response of the atoms around them, then you can make it such that it's no longer transparent where the excitation was. So even though you had a transparent cloud, when they reach this vicinity, this neighborhood around the Rydberg excitation, then they will get absorbed. So this is like an absorptive photon transistor, because what happens is that with a single, now going into the transistor analogy, with a single photon, you can decide whether to put or not this excitation. So you send a photon and create an excitation here, and that determines whether this big flow of photons can go through. That's how it works. So a single photon creates an excitation that ruins your transparency. So this is maybe this is an absorptive kind of photon transistor. If you're looking for applications more towards quantum computation, maybe this is not something you want, because in that case, this is just as an aside. In that case, you would want to, in quantum computation, you want to implement unitary gates where dissipation cannot play any role. So in that case, you can also, there's also been other further work, especially by this group, where the Gerhard Remper group, where they implemented something similar, but it's more something similar, but more towards, instead of shooting absorbing the photons away, they would add a phase into the photons, imprint a phase to the photons. So what I'm saying is this is absorbed, but you can have others which are dispersive, let's say. So this is a partial summary of the talk. I have 3 more slides after this one. But so, I mean, this is the main message, that strongly nonlinear medium can be used as building blocks for photon manipulation tools. And that Rydberg's excitations can help you implement this strongly nonlinear medium because they can translate the nonlinear behavior of a single atom into a collective nonlinear behavior. So they're really helpful to leverage the single atom nonlinearities. And I just talked about some of these implementations, what are useful for. And this is just like a show you like a second advertisement of the lab tour. And just so that you know what kind of things are going on. I mean, so far, all of the results and implementations have shown you how they were from groups around the world. We're building an experiment towards that. Also want to play with few photons and Rydberg atoms. And I mean, it all happens in a vacuum system. This is our vacuum system just after being assembled. I'm going to put, this is the vacuum system. We can already, I mean, we can prepare cold atoms in our vacuum system and create Rydberg excitations with these 2 lasers. And let's say, like the simplified version of the experiment is you can send these 2 lasers. I mean, you basically send one laser in one direction, the other laser in the other direction, and we detect the photons. In this configuration, so this is going to be super quick. Let's say I was saying we can send this to the blue and the red beam. If you just think about sending the red light into the atoms, what we measure is we have our atomic cloud here. We send the light and we see how much light goes through. It's a simple experiment. Send light to atoms, see how much goes through. And as a function of the frequency of the light, you can see it's the red line that it will just get absorbed. Maybe, well, let's see. And so with the red light, it will just get absorbed. But once you turn on the blue light, you will get this transparency thing. This is what I was trying to hide when I was talking about the transistor, that you configure your cloud such that the cloud is transparent for your atoms. So this is, I mean, this is what it's called electromagnetically induced transparency. That it means that whenever you turn on a second beam, you can turn your cloud, which was opaque, you can turn it into transparent for certain frequencies. But the point is, these are things measured in our experiment. And the nice thing about this is that you can really, really control the index of refraction of your medium, and you can do like slow light. You can decrease the speed of the light. So, I mean, I'm just trying to show off things we did recently. I mean, we're happy that finally we have an experiment that's starting to look like something we can play with. So we're sending some pulses of light. The orange is a pulse of light we send, and the blue is what comes out. So even we send a pulse of light like this, like the orange one, it comes out later. And so the fact that, I mean, it looks like, okay, 2 Gaussians, but the light comes so much later that it means that the speed of light inside our atomic medium, which is super small, well, it's a few millimeters big. It's around 900 meters per second. So it's already something, I don't want to, I mean, I'm not sure. I think airplanes can go faster than this, but I don't want to put my hands on fire of that, for that. No pongo las manos al fuego. But anyway, I mean, we hope to even go further and even store the light and do some nice experiments with this, because these can really amplify the effects of the interactions. But anyway, this is like the team, and we collaborate with a lot of people here, and thank you very much. Yeah,
Questions for
maybe
Asaf.
in 30.
Questions here.
Thanks. When you talk about the single photon server, how do you introduce the noise to your system?
So what we actually do is not take it away. So there's always noise because the atoms are hot and they're moving around and they're colliding. So maybe working with there's some strategies to further increase the noise. So what we just did is not do anything. Don't worry about the noise. Leave the noise that is usually there because of movement of the atoms. So that means maybe don't cool your cloud so much. Maybe don't, but you can even go further and introduce noise. One option is to use these speckle patterns from lasers. That's an option to add noise. Yeah.
Yeah. Thank you for your presentation. My question is about the second order correlation function. You show that you have more atoms. The second order correlation function close to zero. But what happens if you continues at what is the limit, for example?
Yeah, maybe I need to clarify. So it's not going to more atoms, but exciting them more. So going to more excited states. So when I was showing the structure of rubidium, it's like instead of going to n equals 7, you go to n equals 50 or n equals 100. But it's a good question that what happens anyway? What happens when you go further, no? If you try to excite them more, it starts to become very complicated experimentally to go much further than this because of this number here. The polarizability of the atoms grows with n to the 7. So that means that the higher you go in n, your atoms are more sensitive to electric fields. So then if you go to n equals 200, then you have to worry like, maybe I'm wearing nylon today and the experiment doesn't like it because it will affect the atoms. And so you basically start to become paranoid because you literally need a tinfoil hat to get rid of static electricity. And so it becomes more difficult, more challenging, and you need to have more control of the electric fields. Yeah.
In of the talk.
Yes, actually, I mean, that's a bit more involved, but there it is. I didn't actually have it in the talk, but I mean, this is a way to go towards that. I mean, what I was saying is with EIT, with electromagnetically induced transparency, what you get is that first, I mean, like you do it in many steps, but you start with an opaque medium, like without the blue light, you have an opaque medium. Then you add the blue light, and at this frequency, it becomes transparent. Then the Rydberg interactions, I mean, this is just any three-level system. Any three-level system behaves like this as long as, well, let's say any three-level system, almost any. Once you introduce interactions to this system, the interactions between the atoms map into the interactions, I mean, the light travels inside the medium as a superposition of an atomic excitation and light, and a field excitation. But these, I mean, what they call polaritons. Anyway, the light travels through the medium as a combination of this, and then when you introduce interactions, it means that your photon effectively interact in the medium. And then you can arrange it such that if two photons are too close together, maybe they will ruin this transparency. And then if they're too close together, one goes away. So you have to send like a lot of photons into the system and only one goes away every time. So it's something like that. I would need maybe more time to explain it carefully, but it can be implemented. The question is how ordered can you make it? Yeah.
Hi, I have a question. Is possible to make a absorption that is specific a number bigger than one of photons?
Yes, thank you for the question, because I mean, this is maybe cheating, but you can do it. I mean, here you can have like an array of single photon absorbers. So this absorbs one, this absorbs two. And if you put, I mean, you have to have like two isolated blobs of atoms, and each one works as a single photon absorber. But it's actually, yeah, thank you for asking, because I skipped through this and now I can explain it. That once you have, I mean, the absorption of the photon is stored. I mean, what happens is that it stays in the atom as a Rydberg excitation, and then that you can detect easily if you apply an electric field. Rydberg atoms ionize very easily, and you can detect the ion. So you can have like an array of these single photon absorbers, and then once you send your light, you can detect how many of these were absorbed something. So you end up with a number resolving photon detector, which is, I mean, there are ways to do them. This is like a fancy way to do them, but they're not so common, but they're becoming more common. Yeah. Now one can buy a number resolving photon absorbers, but yeah.
Thank you.
Atom field interactions. Have you tried to use density dependent model like
Like the one, I didn't hear the last one.
Luxicuma, for example?
I don't know.
In general,
But what I can say is, yeah, I mean, there are models that, I mean, what's challenging here, I think, is that to model situations where you have many interactions, many excitations in the system. But intensity, I mean, for high intensities, it's become complicated. It's like a many body system, and it's very difficult, I think. But you can definitely do like the modeling of exactly how pulses propagate. If you say if we have a few photon pulses, if it's like time dependent pulses, but when you start to have many photons, it's become messy and difficult. Yeah, it becomes like a quantum many body system.
All right, so let's.
And I want to thank everyone for still being here awake. Mostly those of you who come from abroad. Let's thank all of our speakers for today. And you, thank you so much. See you tomorrow morning.